Good morning, everyone. I hope you're all good. Let's just see if we're live. Looks like we are. Whoops. Not yet. Let's not end immediately. Let's try not do that. Let me just share this with the Discord. That'd be not good. A 4-second live stream. Okay, so we're gonna do some programming today at the beginning of the live stream. I have tried to fix my playlist of just general music. So hopefully that doesn't work. Join in. Thank you for bearing with me while I set things up. Once the chat has... Oops. Alright, fantastic. Looks like we're good. Let's see. Pause the timer. There we go. Look at my excellent thumbnail in GIMP. Not pause the timer, sorry, get up the chat. That's what I'm trying to say. So yes, we're going to, once the chat has loaded. There we go. Thank you. And there we go. Okay, so, yes, I think I said this last stream, but I was struggling to do... Very good morning. If it is day to you. Yes, it is, Alex Coates. So I think I said this last live stream, but I remember struggling to code anything when I left the coding to the end of like the 7+ hour live streams. So to make sure that I don't fall behind while I'm studying like lighting or whatever, we should try and keep up with what we end up doing. Maybe not for as long as like say 7-8 hours in a row, but I think it's going to be useful to at least do stuff in this engine while I study. Otherwise I'll be really good at ray tracing or whatever we end up studying today, and then I won't know how to code anything in C++. So the first thing I'm going to do is restore my lighting calculation in the BRDF and leave this until I actually understand this a little better. So I don't know what I'm going to do with this. I'm probably just going to delete it, I think. And just kind of restore things back to the way they were. Use the old BRDF algorithm I was using. And all the other Fresnel mixing things for the lighting source. We will be able to do this better once we get better at lighting. So, oops. So hopefully we'll do that. The goal of the stream anyway is to do more with the physics engine that's currently being done, which I can show shortly. So the physics engine is able to find a object and collide with it, no problem. So roughness factor doesn't exist apparently. Oh, faster but less accurate. Actually, we want the other one. We want the slow one. Whoops. And that should be the lighting, apart from that minor change. Let's get rid of this. Alright, so that's our basic fragment shader, kind of back to the way it was. Ignore all the squiggly reds things. Do you have any C++ roadmap? Hi, Telepathy. Are you talking about learning C++ or stuff that I'm going to do in my game engine? But yes, I can answer both if for either question. So that should be that. Okay, so I think we should have at least a compiling / the old lighting system for our yes. Okay, so this is the old BRDF that we're trying to work with the intensities really high, and the normals that are being calculated on a particular object are quite wrong. The specular and the diffuse have a bit strange look to them. In fact, I probably need to make sure as well that this... I think it's a bit loud. Let me change the music one moment, guys. Let me just make sure that's quieter, because I know sometimes it gets really loud for learning C++. Okay, so what I would recommend if you're learning C++, this great website that I went through, by the way. So I'm not telling you to do something I haven't done. Learn C++. This has been continuously updated throughout the years. And if you just go through this, it's completely free online. You'll be generally pretty solid with your C++. I should be able, if you earnestly go through this and you understand it, I should be able to quiz you on C++ as a junior level software engineer. So if you understand this, I should be able to say, you know, I don't know, what's a virtual base class? What's the, and then I'll be able to go, if I want to overload the unary operators, how do I do that? What's a C-style string? What's the this pointer? Etc. All these type of things that junior programmers should know is all in this section. And this should help you develop your C++ skills so you can basically do what you want in, you know, if whatever software you want to develop, right? You don't necessarily have to do the... yeah, just the further you get through this, the better, basically. And it assumes no knowledge as well, this website. So it's like, what is C++? What are these tutorials used for? So it's literally like, you know, C++ was developed by C was developed by Dennis Ritchie at Bell Laboratories, blah blah blah. So it assumes that you've literally never heard of programming before, and the tutorials are quite short. So yeah, go through that, and you should be pretty solid for learning C++, I think. And then you can because you'll have more experience, you'll be able to branch off and learn different things. Like, for example, if I want to learn something on C++, I can go to C++ Weekly. This is like more advanced. But because I've done that, for example, I could just randomly pick, I don't know, using string view, span, and pointers safely, right? That would be like a more advanced tutorial, but it assumes that you've basically read everything and then learned CPP to understand this kind of stuff. And he's done like thousands of these videos where he talks about something every day. But anyway, yeah, that's what I would do. Learn CPP, should be good. Just for reference, so I did that in 2017. So the stuff I learned on that website is very different from what you'll learn on the website. Anyway, so let's go into the physics engine. So what are we trying to do today? When we collide with an... Oh, actually, I need to change the play camera. Can I just bear with me just a moment? Let's close this. Oops, I keep forgetting that I've done this. Change. I think what I'm going to also do is pull the changes that I accidentally pushed to master on in Linux as well. So we'll see how that goes for our merge collision. That might be a horrendous situation to deal with, but we'll see. We update the player. We update the player with the camera. Yeah, no problem. I'm glad it was helpful. So we'll do this. So that means we are controlling our player with the light source and stuff. So, and we have a deleted thing here. Oh yeah, bunch of redundant programs. Okay. Okay, so this is where we are typically if we have a player, and when we crash into something, we make laser sound effects. But what I want to at least be able to do, or at least start to be able to do at least, is be able to delete the geometry when I crash into it. I think it's one of the simplest things that I could try and figure out to do when it comes to interacting with the game itself. I don't really care, like, you know, colliding into anything in particular. But what I'm going to make sure is that when I collide into this and it's not the player, that we delete the object. So that's what we're going to be trying to begin with. I don't know how long that's going to take. But yeah, it shouldn't be too difficult, but we've got to use Jolt's indirect pointer kind of management system. So, and yeah, I'm also just going to grab on my GitHub, before we even start, actually, let me just start this as well. I did some change on Linux a while ago. Oops, I keep doing that. I bookmarked a old GitHub thing that I barely ever use. I'd never use anymore. Right, so go to void. Yeah, and thank you for all the stars, by the way, in my project. It's I don't exactly know 100% what they do, but very much appreciated. It shows that at least you're interested in the project, I guess. So what was the last commit? That's what I'm interested in. So this was updated a month ago. What are we doing with lighting today? We are going to do programming first. So the order of things is going to be program, study for hours and hours and hours, like we have been with the book, which I'll talk about later. And after that, we are going to do a bit of revision at the end of the day. I want to reverse the order of things that I've been doing, where I've been programming at the end and I get really tired and I can't program anything because I'm so half asleep. But I think revision is an easier task, right? But we're going to be doing the physically based rendering book. So more ray tracing. I found a good resource though, if I just talk about that briefly. The resource is a ray tracing tutorial series by Casey Moratori, which is going to be really good because he shows SIMD and multi-threading, which is something I need to get better at. So outside of just ray tracing, I think that's just going to be a general good software project to pursue. Yeah, so I'm going to probably do that off stream just because I'm pausing a video and coding for 5 seconds and then listening to someone speak and then pausing the video again. I think it's going to be a bit time. I don't think it's going to be a pleasant viewing experience, but we'll see. Okay, so it's saying, the big loose goose. Yes, I'm very close to 2K. It's exciting, actually. I think it's a big milestone for my YouTube channel. I'm quite excited to see if I can actually get to that. But we'll see. It's one of these things where it seems like the only thing that's updated is the vendor, which I assume is just line endings. Yeah, I don't know what's changed. I thought I changed something else. Let's go back. I might be lying here. Yeah, I don't know what I'll do for that. Maybe we'll watch a movie together or something to celebrate when we get to in the Discord to 2,000 subscribers. Because it has taken a year to get a year from 1,000 to 2,000, which has been pretty tricky. I think I'm pretty sure that all this stuff down here is just line endings changing. Yeah, just between Linux and Windows. Or something like that. I don't know. It seems like a lot of stuff's changing. But anyway, it doesn't look like I thought I committed something, or maybe it's still in Linux. I'll have to check another day, I think. If it's not in Git, then I don't think anything is that anything in that is anything here. Oh, by the way, with the subscribers, I don't take anything for granted, by the way. I'm very grateful even for having 40 subscribers, so getting to, what, 1,950-ish is super, super cool. I still think it's like a big number of people that are interested in what I'm doing. You know, that's 1,950-ish people telling me that, yes, I'm interested in what you're releasing video content-wise, that I want to watch more, which is cool. So, you know, thank you for anyone who has subscribed over the years and or just recently as well, and has supported me. So, yeah, very much appreciate you all. Regardless of how small or big you consider my YouTube channel, it's a blessing to have people like you guys in the community. So yeah, it's right. So I think we don't need to worry about what is it called? We don't have to worry about the Linux thing that I was thinking that we need to implement. The next thing I need to, so basically we're gonna tackle the main task of today then for a while. I'm probably going to do this for at least till lunchtime, or maybe, well, at least two, a maximum up to lunchtime. And then we're going to read a book for like the rest of the time, which is probably the majority of the time, and then do a bit of revision at the end. Okay, so What have we actually changed in our shader? Okay, nothing crazy. We removed some redundant stuff. Let's go into the physics. What I'm looking for is on contact, right? So this is the... It never... For some reason, body 1 is never the actual collision. Body 2, sorry. I don't know how that is the case. But effectively, we have... the way we're doing this, anyway, is because we have to use this, like, get user data, which is effectively a pointer to... It's a void star pointer, effectively. The Jolt physics engine is treating it as a uint64 number, but back to my favorite bug club stream. Hello, hello guys. Thank you for all joining us. Bug club stream. Yeah, it's we're gonna be doing that later for sure. So I won't disappoint with that. But yeah, doing a bit of coding for a bit, so I keep my yeah, starting earlier and earlier every day. Yeah, let's go for a long stream, eh? The only thing I haven't done, which I just realized, I haven't made my lunch, so I'm probably gonna have to like go BRB for a bit longer at lunchtime. But we'll be fine. We'll be fine. Yeah, thanks for joining us, guys. So the physics engine that we're dealing with has this get user data, right? So effectively, when we set up the rigid body, this basically has we can set some arbitrary pointer to some piece of data. And we then basically figure out, is it not 0, which would be the equivalent of null in this case, and then we cast it to an entity, and then based on that entity cast, because that's what the pointer is, we do a reinterpret cast here, and then we can figure out the entity type, and based on the entity type, we can do something with that. So what I want to be able to do today is, based on that entity type, I want to be able to delete that particular entity. Or at least do something a bit more interesting than just make a sound effect with the player. I mean, I think that's still like a useful thing, but we need to actually at least like have a rock entity maybe. So what I might try to do today is begin with thinking about the game itself and what entities we need at the very basic level. So yeah, and I think we're going to have a rock entity to begin with, and then we can cast that based on this void star to what we need, and then do something specific with the rock guy. Maybe that'll help us delete it, or at least look up some ID so we can remove it from a list of things, something like that anyway. So yeah, we'll see. It's going to be a bit of a tricky one to work out. Isn't it hard to code with Vulkan? Yes. Yes, generally. I can't lie to you on that one. Vulkan is difficult. But in my opinion, Vulkan isn't as hard as people make out. What makes Vulkan difficult, I think, makes all graphics programming difficult, is that it's graphics programming. Graphics programming is very difficult. So it doesn't really matter if you pick DirectX 12 or Vulkan or even OpenGL. The more advanced graphics that you want to implement, the harder the code that you have to write. But yes, Vulkan is difficult. Vulkan is difficult because it's an explicit API, which means that you have to explicitly define everything. Meaning that if you want to, for example, do something very simple like render a triangle, you have to explicitly tell Vulkan what to do in every single little step along that way. Meaning that, yes, there is a meme out there that exists that it takes just over 700 lines of code to render a triangle in Vulkan. That is because you have to be extremely explicit with what you tell Vulkan what to do. And that makes it difficult, because OpenGL did a lot more hand-holding when it came to your code. So let's see. I probably don't want an asteroid class, maybe. I don't really know. So yeah, that's why it's difficult. But unfortunately, even if you choose OpenGL, you still have to deal with the fact that you're doing graphics programming, which gets harder, no matter what. Asteroid. Because it's like computer science mixed with like maths, applied maths, if that makes sense. That was my Windows noise, not you. So we end up with a you end up with a lot more stuff that you have to learn. Sorry, that's also me for Windows noise. I'm not trying to push you down into a rabbit hole. No. Yeah, exactly. Yeah, Ratchet. Ratchet's being a bit sneaky there. I love it. 700 lines of Vulkan code will give you 700x more control over things. Well, I wouldn't say 700, but I get your idea. I think you're doing a bit more of a joke there. But that is the upside of Vulkan. You do get more control in theory. But a lot of people who start with, graphics programming are kind of like, I don't care. I just want to be able to do this, and it's like really difficult regardless. So, yeah. Asteroid. Did I say .h? I think I did. Got me yapping and I didn't. Yeah, generally, that's my Windows noise. Sorry. Generally, I've heard it's a good idea to use CPP because your build system knows 100% of the time what you mean, rather with .h, which could be C or C++. Not that it's a big deal. Did I spell asteroid? I feel like I'm spelling this wrong. Is this a game engine? Yes. Asteroid. Okay, so it's ES. Okay, so yes, I did spell it wrong. Excuse me. Yes, I don't think you've been around for me coding because you're kind of new to the streams, but yes. Most of these streams have been studying lighting, but there is a reason for that. I am trying to build a game engine around that. Okay, it's only like 20x. Yeah, I would say it's like 20x. Yeah, that's you get a lot more control. So yeah, if you're interested in this game engine, the source code is in the description. It won't run for you because I've hard coded some assets, which I'm not uploading to Git. Because uploading binary files that are huge to Git is a bad idea. But if you want to see the source code in its entirety, feel free to download it and do something with it, or learn from it. Maybe you'll learn not what to do with my source code. So I think I am going to push this code. I think before we start actually. Asteroid. Because I'm going to do a lot of rewriting stuff, so let's at least get it into a state where it's actually... because it's kind of like in a decent state, if that makes sense. It's not like... with great power comes great responsibility. From yesterday, I had joined you. Yes, so it's completely fine to ask questions, by the way, about these type of things. Thank you for joining us, as well, Bot Red Gamer. So I'm just going to push this up with the small change. Although I've added some files, I don't think it's that bad. So added some empty files and improved the overall structure of the code base. Yeah, in theory you could make it's much easier to make Vulkan multi-threaded than something like OpenGL. But yeah, like I keep saying, most people who are starting out don't really care about that kind of stuff. So, oops. Oh, I put the I in the wrong place. That's going to be a funny commit. technically my code does not compile, and now it's on Git. Never mind. Oh well. Okay, so what do we need to in this class? I need to think about this. Yeah, I don't even know what multi-threading OpenGL would be like. I've never tried. Dang, I got bitten by a bug, I've just noticed. Okay, so I'm going to call this rock, just because it's easier to kind of type out and stuff. So we need some, like, rock behavior. And I'm going to make it an object so we can reference it. Yeah, it's a bad idea. I will believe you on that one. OpenGL was designed in the 90s, so it back when threading wasn't a thing. That's why it's hard to do. So design-wise, what do I want to be able to do here? I want to basically do a cast. And I think at the very least what I need to be able to do is delete the object from... this is going to be kind of tricky because... if I go to my physics look again, yeah, we have the in-body pointer here that gets reinterpreted casted to an entity. Entity type, data, we have an object here. Okay, so at the very least I need to be able to... Oh, that was it. I wanted to make this like a bigger class, a bigger deal. Alright, so let's at least make more than one object. I think that's going to be useful. And so let's see the design of this. Yeah, so when I make a rock, I need to make it via its own object. Rather than just like sticking stuff on an array that then... So my idea is effectively, let's just kind of use paint. And I will kind of like design this. And this is not for, this is for people watching and also me, because I need to kind of think about this a bit. So don't feel like I'm babying you. I actually do need to think through this. So let me read the chat just before we begin. There's like one safe way to do multi-threading texture uploading, just like the pixel part, but it's very convoluted. Oh, I see. Okay. What other projects have I made? So what are other projects that you made in the past? So yes, they're all on Git, but I've made many different things. I've made text-based games. That's how I started out. I have made a bunch of other engines that are on my GitHub. So, okay, so we have I'm going to say a green, because I always think entities are green. So this is our entity guy. So this could be anything. Whoops. Yes, fill. And... also green. So I'm just gonna like go to this and kind of like entity entity, whatever. I think that's how you spell. I'll just call it ENT, right? Run it once. I want to see how much progress you've have been done. Unfortunately, it's not that much. I have been mostly studying, so Heisenberg. It's pretty much exactly where you would expect it to be. But I'm trying to do some stuff today with the actual code rather than just yeah. So we're back here again. So it's not too interesting, but we are gonna try and do stuff today, coding wise. Bro, you are too OG. 11 years on YouTube. Yeah, I've been... Your channel's older than me. Dang. Yeah, I've been on YouTube since 2000 and... I have other YouTube channels which I completely lost the time. But anyway, let's think about this. So I have a rock. Okay, and I'm going to. Oh, it's just player, I guess. Maybe I should use UML. This is probably going to be faster, actually. Yeah, let me deal with. I wonder if omelet still works. Okay, let's see if this works. Fingers crossed. This project is yeah, TT's completely correct. Okay, so this is going to be easier to deal with. Okay, so we have a entity thing. Thank you. And we have a player. And we have, now we have an asteroid or a rock. So, calling omelet is, yeah. What is your workflow for learning new stuff? I would recommend making sure that you take notes. I use Obsidian, so if I go in here, I take notes and I reread them. People have been pretty familiar with this, I think, if you've seen me for the past couple of days. So, for example, I've been learning about graphics theory. I learn all this stuff. I make notes, like what is stochastic progressive photonic mapping, and then I work, link all these things together so I can get better at, all this kind of stuff, and then I can implement it. And there's Vulkan stuff. It's good to have each a project that you can work with. So I'm gonna have let's get our omelet guy going. Whoops. Okay, so you'll notice my mouse double clicks a lot. So this unfortunately is, in fact, come on. No, it's the other way around. This would be. So let's just see the properties of player, right? So let's just grab them. I'm not going to write any of the behavior, just the properties. So yeah, learn projects, learn your language, then you should be able to do more advanced stuff. Yeah, UML. I'm making a quick UML diagram. I'm not object-oriented pilled right now. I'm just it's just gonna be a nice scratch pad to figure out exactly how to do this, because Jolt physics has made it very weird for us right now. We are quite limited on how we can interact with Jolt physics with our objects. We have to do it via rigid body data. So I'm going to try and figure out how. Okay, so player movements, we have player settings, we have character, and I think sound effect is probably appropriate here. And this is referenced by a void star, so this is a void entity data. So let's grab everything out of our entity class and kind of build that up. You do two streams a day. Unless the stream crashes, I do one. But yeah, I've been doing some more in-depth streams. Write your own DoD-based physics system. Should take 3 years. You probably on it. You say 3 years. I reckon that's still an underestimation about how difficult physics engines are to write. Like that. I know you're joking, but honestly, I've written a physics engine that took 4 years to write, and it wasn't very good. And that was a long time ago, though. So if you're wondering where a lot of my time went when it went to programming, a lot of it was learning how physics works. And learning that I never want to write my own. Yeah, I wanted to say 10, but I reduced it. No, I think, yeah. 10 would be everything altogether. The physics plus graphics. And with limited libraries. Kind of like what John Blow did. At my skill level, anyway. Anyway, so where's the entity class? Where have I put that? It's in scene. Where is it? It's So I've refactored my code recently, and I can't quite remember where everything is after spending a couple of days just reading books. So I can go to my physics engine and just kind of figure it out to where it is. Work backwards. So where are you? Oh, you're in utils. Okay, so this is what our entity is. Let's throw that in. And let's get rid of the comments and stuff like that. Okay, it's really slow. Why are you moving so slow? Okay. Okay, entity. So effectively, this is how it's working right now. So I'm going to just like put some stuff in here. Maybe what I'm thinking anyway is to kind of like be able to refer back to this entity thing. Okay, so the arrows go in this order. So I'm not going to be able to write a proper UML thing, by the way. So you have to bear with me. So if you guys are like OPP pilled and love the UML diagrams, I'm not going to be able to replicate everything that you guys can do. Okay, so so this is the entity data. This is how we refer to it. Okay. Okay, I guess I could do this, or just get rid of the arrow. Yeah, I've removed all the Final Fantasy VII music from my playlist, so hopefully we don't get copyright strike like we did last time. But we'll see. Oops. Okay, so entity data refers to these guys. Now I think what I want to be able to do is kind of refer back again, because we need to know what index point we're at. So what I'm thinking is hello brother, long time. Was busy with my hectic school life, so I missed a lot of the streams. How are you doing? Yeah, not bad. Yeah, I've been doing a lot of studying, so you've missed a lot of book reading rather than studying. I hope your school hecticness is chills out and you get a bit of a break. But it's good to take your school life seriously, so that's actually a good move. So what I'm thinking is kind of like a uint entity index kind of thing. And this tells us basically the index of which we are in, because this thing is an array of. But I think what I want to be able to do is entity index, kind of like this. Because what I want to be able to do is use that, I think, to delete itself from a list. This is my idea anyway. So if I take this. Yeah, it's good to see you again, by the way. Pure gameplay. So I'm just going to grab this and make this an array of entities. So I don't really know how to do this in a way that's like clean, but basically I want to have this system where we use the entity index to deal with in our omelet programming. If I just make this a little kind of like this and like this, move this up. Okay, so how do I do this again? This is just simple text. Okay. Entity index kind of like refers to this. Entity index. So then we can mess around with the array, which has entities in it. So entities, that's the entity struct. And this is a one-to-many relationship. Let me throw this in here and kind of build this up. So let's get rid of the text. Okay, so this is a 1 to n. No, one go around. This will be the 1 to n. And this would be, I always get this backwards, so you're going to have to excuse my rubbish UML-ness. 1 to 0, right? Oh, why is it changed? Okay, let's change these around. What? Hello? So there's n entities and there's one array. Yeah, okay. That's the relationship anyway. So effectively what I want to be able to do is set up a way to mess around with the array of entities based on an index that indexes entities. So my idea anyway is to use this index, because the reason I'm having to do this, by the way, is because Jolt only allows, so if you decide to Jolt, yeah, I'm gonna say Jolt only allows me to reference things by a pointer. So it's more like this is more accurate, actually. So actually this is more accurate than what I wrote earlier. Because this is how we're accessing the actual object via the entity data. And then what? Oops. Excuse me. My mouse is the worst when it comes to UML. I'm very object-oriented build. I haven't wrote a single virtual class. Oh, sorry. I'm very OPP build. I think that won't happen. I've even wrote one singular virtual class in my renderer. Really? I haven't actually looked at. I've looked at parts of your code, but I haven't actually seen like a big chunk of it. So the idea here is that I hope that when I say delete something, I go entity data, entity index, index goes into here. We remove something from here. This reduces by 1, and it doesn't. The Jolt physics engine with its threading, multi-threaded access. Oh, fair enough. You just got just a general. It's just the camera. That's virtual. Fair enough. I have actually more than that. So I guess I'm object-oriented build more than you there, Ratchet. So we have Jolt, that refers to things by data, then we cast that to a rock, then the rock goes in here, and then goes into this, then deletes something from the list, and hopefully this gets removed without breaking the physics engine. So what I don't want to happen is a race condition. So there's a possibility when I try to remove something from here that when I do that, everything kind of falls apart. Oh, also you can add various modes of cameras. That makes sense. I mean, I have just functions to do that, but I think it makes sense to have various kind. Like I have a player camera, which you've seen, and a free floating camera, which I keep having to switch between. All right, so that is my idea. I don't see, unless people go, no, this is not going to work. This is what I'm going to try. Yeah, so the idea is that we can delete. So goal, and if I add some random text there, let's add a note, I guess. I've never actually used this before, but let's go with orange. Goal here is to be able to reference an object from Jolt, then use that object's index into an array. Okay, let's break this up into little bits. Let's go with, let me just reorganize a few things. Write it into sentences. Reference objects via the rigid body by the rigid body. Cast that. I already got this part done. Cast them to the type I care about. Then use that body object's index in that references its position in an array. I'll make this bigger on the screen. And then use that index to do some kind of deletion. So we don't have stable arrays yet, so I don't care if a delete swap kind of breaks everything, so we'll just use an erase for now. But that's the system. So we cast. So the 3 steps. So we get a collision detection from the rigid body. We get the user data. We cast that to whatever type we are. We use this index to go into here, and then we delete something that's from this array. The final goal is no crashing, obviously. No race condition / crashing, which is kind of tricky. All I need from a camera for rendering is the position and the view matrix. Doesn't really matter. I see. Those are which calculated. And you have a lot of cameras, so I use this dynamic dispatch. I could technically use static dispatch, but that makes sense. Yeah, makes sense. Yeah, what you're doing there. For me, it's kind of like a basic approach. Until I need more cameras. We'll see if I need more cameras. I don't know yet how many cameras I need. Maybe there's some graphics theory that I don't understand, which requires a special type of camera. But for now, that's what we got. So, okay, so we need to we need to store some extra data here. So, again, I'll just call this entity index, and maybe set this to uint 32 max. Oops, not 43. 32. Or 432. That's not good either. So now we want an asteroid, which is just called rock. And this at least needs, at the very least, let's get out caps lock. We are still listening. Thank you, YouTube. Mike Acton after he finds out I use one. Yeah, he'll give you the angry face. I get the reference. I get the reference. Yeah, it gives you the frowny, angry face if you use virtual classes. Foundation. Yeah, he would do the same to me. Well, I think every type of programmer would. I don't know what my code is. It's just kind of like a hodgepodge of different techniques. What did I call this thing? In the foundation called it's platform. I remember now. Okay, so at the very least, we just need to include that for the different includes, basic includes. Okay, so when we create a rock in scene, we just kind of throw everything in an array, which is fine, but we need to reference that back, unfortunately. So we do have to move to more object-oriented style because of the physics engine. But that's chill. I'm not going to cry over that yet, anyway. Okay, so what do I want to keep in? I don't really care that much about what's in the object as long as I have a reference back to it. So what I'm thinking of doing is yeah, let's grab. So I have a struct here. Now, should the rock own its own data? That's the first question. Like, this stuff is very rock related. I think it makes sense if we're going to have an object of data that we need to have like some initialization code. This is to try and not have this class this function so overloaded as well. That's a big motivation behind this as well. It's very overloaded, this function. As you can see, it's like pretty dense. And it's eventually going to have this system where we have to send in the actual entity data. You know what you could do? Actually, we could actually not touch this at all. Hang on. What I need... I'm going to try something else for a minute. Making my 3x, the vec3 class abstract. Yep, 5-head indeed. Yeah, for every single dimension you've got to expand out another float by virtual base classes until you get to the largest vector possible. And then of course you've got to have a multiple inheritance to figure out matrices that go off in column order as well. So yeah, anyway, need an abstract vector builder factory, exactly. And we need a factory builder for that factory builder as well. Okay, for people who are like, what are they talking about? We're kind of making fun of the fact that you can end up in object-oriented programming down like a bit of a rabbit hole of over abstraction, which means that you can do things silly like a float would a vector of 3 points would be x, y, z, right? And it would be very silly to do anything other than just have a struct with just x, y, and z in it. So yeah, I know some people are new to programming, but I make the joke accessible to you guys as well. Yeah, don't do that if you we're not discussing good ideas here. We are making fun of stuff. Okay, so what I'm going to actually do is when I cast this, the thing I need to do in this physics engine, right, is... Where's this come from? Okay, so we do have a rock. So what I want to do, actually, instead of having a null in the scene creation, I'm actually going to try and avoid this struct guy that I've just created. I know I just created it, but maybe there is a way to simplify this with the data I've already got, and that's what I'm going to try and do. Because I really would like to work out. Obviously, adding stuff is fine, but if I'm adding stuff unnecessarily, then it gets to a point where it's like, ugh. That I'm doing stuff. So case entity. Oops. Type. All right, break. Okay, so what I'm going to do here is grab. Why is default like this? Yeah, this needs to be null. This needs to be its entity type. Okay, so not player ID. What's body ID? If entity is not equal to player, then do this. Okay, so this is clumsy. Let's try and combine these two together. I'm going to move this out the way because I feel like I've got an if statement and a switch statement here that could be combined. Avoid templates virtual maxing, yeah. I love it. I love it. Exactly. That's what I was thinking, right? You gotta inherit multiple times to expand out columns. This is very good design. And not at all it's insane. Okay, so if I've come in with an entity type of player, then I don't want to do this. I want to do this specifically in here. Yeah, so we want a switch statement here. And that allows me to not do this twice, which is kind of stupid. And create body ID. Push that to an array, which is fine. And we allocate some memory. Yes, that's the new thing we have to do. And we do an emplacement new, which I'm very familiar now that doesn't construct. Then we initialize it, then blah 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 blah. We don't need to do this at all because the body ID is just here. And yeah, we should be good. So that's cleaned up that a lot. As far as I can tell, the get shape. So this can be removed. So what are we missing then? Shape. What is this for? Right, so we need yeah, we still need this, I believe, as far as I can tell, all in. So what I'm actually going to do is put this at the bottom. This is going to be kind of interesting way of doing it. So this is going to be true for all entity types, and what I want to do is take this out and paste this in here as another type of switch. So this is likely going to be a function in the future. In fact, it's probably a good idea to put this into a function now, despite it only having one object type, just to reduce the overloadedness a little bit. So void select collision geometry. No, type. It's not going to be void, is it? Okay, that's a terrible name, but let me think about that a little bit more when I actually get the type we need. I think get shape is probably better. Get collision shape. Yeah, I think that's probably appropriate. That we need to return whatever this is, which is just a map 4. Fantastic. Yeah, so this will just help us like make readability. So get collision shape. We're probably gonna have one argument, which is the. Go back to here again. We need to tell us what type we are doing, and in this case, we're gonna say we're gonna take in this fella. I think it's just an enum. So let's have a look. Yeah. Okay, so it's very nice. We can just do an enum here. So shape type. Okay, fantastic. If you throw this in, I'm going to put it below here because this is kind of like a... This would be a private function, but I don't use encapsulation, so ha ha ha. We aren't doing that. So this will help us stop repeating ourselves as well because we're going to use this multiple times. This is all around a good idea. The thing I really like about object-oriented programming is the do not repeat yourself aspect of things. So we need to steal you from here, just so I can... I'm stealing this with a cut rather than typing it out so I notice the errors. I have a feeling that I could just literally return in place return. So I'm going to do that instead. Get subtype. We don't need to do that because we have our array that we're going to do things over. Shape settings. Ah, right. Okay, so we need more than that. We need these shape settings as well, unfortunately. This is because the shape settings is separate from... yeah, we can get rid of this now. So yeah, unfortunately the shape setting is separate from the enum type, which is making things a little clumsy, but it's not too bad. Exception-oriented programming, all control flows done through. Oh my goodness, can you imagine? Making everyone happy, everyone unhappy is what programming is truly about. Exactly, right? Now, if you can start a flame war on some forum / Reddit, you've done your job right. That's what it's all about at the end of the day. How angry can people get? It is true that we'll know the setting object. In fact, maybe instead of passing it around, I assign it to an object, some data, right? Because here we just kind of stick it on the stack and we pass it from function to function to function. Yet we have... I don't know if that's a good idea. The reason I'm saying that is... how many shape settings are we going to end up having in one place? Alright, so the jury's out. The jury's out even on what, if this is even good. So... wet is better. Wet. Wet? Well, I don't even know what that is. You've gone too deep. The references are going over my head now. I can't follow you. You've gone too deep. See, the jury's still out on it. I think we're at least very much cleaning up enough anyway, so... Okay, so we actually do need this map 4, but we can just say shape. JH. So R map 4 shape. Was it model? Equals JR R matrix S identity. Alright, so that should at least give us something if we get bad data. Okay, so now we need to run the... do this with two objects. The shape setting. and so this would be JPH shape. Write everything twice. I like that. Write everything twice. Yeah. Window entropy technique. I see. Both are valid. Yeah. I think it's the Ratchet's version is just a more abstract version of what you write everything twice. Okay, so what is the enum called when we're doing this? It is this guy. Yes, I'm copying too much there, but that's fine. Okay, so sphere, right? I've deleted these shape settings. Yeah, so we are passing a shape setting around, and then we can actually set this to this, and we're good to go. Which means we can basically do the same here. Very nice. Look at this. Oh my goodness. My code is not as bad. Okay, so we basically need to do the same deal though for this. It might be good to... Okay, what is the difference here? So there is going to be a difference depending on the type. I'm going to see if I can get away with doing things once. And only... So we'll probably pull these out because these are duplicates. We do need to do this differently. So rock... Oh, we don't have it here. So include... So this is the idea anyway. The... Okay, so... I'm going to be doing something very... Create physical device. I assume it's with the logical device. Create physics. Yes. Oh, you said create physics, not create physics device. Oh, yes, that's what I want to do. Okay, so what I'm going to be doing here is allocating some memory for a void type and then casting it on the fly. The problem is I don't really care about that at all. Okay, I'll just roll with it for now. At the very least, it will... So we need an inted function, I guess, which we don't have in our case. So let's write a empty inted function. This is effectively my version of a constructor. It's not going to do anything. Because I'm going to try and work around this a little differently. Oh, yes, okay, so this does that. And now we need the body ID, which is this. Okay, so set user data, which is different from, which is the object we just allocated. Now we're doing it the entity, so we can cast. We don't need to do this twice. What we do need is entity data, and okay, so let's pull this out to reduce some more code duplication. Can put that there, and we should have the body ID by that point. Yep. Let's get rid of this. Okay, cool. So yeah, now the only difference is the dynamic, the object. Is it dynamic or static? And the user data by the looks of things, and that should give us a rock type to deal with, and at the very least now we should be able to break on, let's close that. We should be able to break on a collision detection and figure out we have a rock. We'll have to check to make sure that we haven't just nuked the engine, but we'll find that out in a minute. So I want entity type in here instead. This got confusing for me as soon as I looked at it. Okay, so this is just for people who are wondering. I've set up this behavior, right? What are we doing here? We're doing this line here. These arrows are what we're doing. But I realized that we don't actually cast directly to an object here. So this is slightly wrong. My mistake was, let's close this for a minute. My mistake was assuming that we cast directly to, we actually don't. We cast to an entity, which is different. So the actual way this works is this, which if you're familiar, let's try and rearrange this a little bit. So I want to put this here. I'll fix this up in a minute. Yes, the arrows are all horrible. But effectively, yeah, so let's move this over a bit more, I think. And kind of improve the lining. Something like this, I guess. Yes, so I can put this here now. Like that. And sorry, I'm faffing over with UML, but it's gonna be useful, I think, because this is gonna be the So actually, that's what happens. Jolt. Let's get rid of this. Jolt converts from my cast something into an entity. So this is more accurate. Let's get an arrow. This is how it works, and this is done with get user data, right? Let's make this into a function. That's how it works. Let's get rid of this arrow. At the moment, anyway. Let's move this over here. Very nice. Okay, so for deleting, you can just not check the entity type and destroy it via its entity index. That's exactly what I've been thinking, right? So instead of doing like this roundabout, I could literally just be like, you know, if I was to do a delete, instead of, that's why I was like, wait a minute, I don't need this really. So this is the delete method. Actually, to do a delete in UML, you need to do, well, to do a function anyway. Where is it? It's, yeah, it's a state change. So to delete, it's kind of like if I want to do a delete, it's kind of like all we care about is let's put this like here or something. And we actually only really care about the entity index, which is found in here. Look, this guy right there. Can I bold this with this how it works? Yes, fantastic. Okay, so you can see that entity index is bolded, and then that state change goes through here. So this is a state object change. Actually, I could just do it like this. Then I can delete the thing out of the array. I don't really need these references. So in theory, I don't need these arrows, and I can actually get rid of this for deleting anyway. It may be useful to refer to where we are, but that's like, that's how I should be able to do these things, right? If I need specific object access, Yeah, I know. Uint 32 something. I don't really know what's going to be in rock. I might even remove it, but yeah, that's the idea anyway. So we'll see if this works. You don't need to yeah, I don't even need to cast it. I don't need to do this cast. This is just this was just here to test if I was doing the things correct. But I do need the enum to tell me what type I'm working with, but that's about it. Are you storing your entity data in Jolt's user data? Yes, I am, but I might not do that in the future. Yeah, I'm gonna have to make sure my thing is thread safe. So I don't know how the access pattern works in Jolt, so we're gonna see how that's gonna run. I hope it completely falls over after a break, but we might get, unfortunately, a deadlock or a race condition. A deadlock would be preferable to a race condition, to be honest. So we have rock. We need to... Okay, so this is the problem with this class. It's very difficult to get data out of it. So for now, what I'm going to do is just make sure that my new system of creating things. Let's... I'll delete stuff in a minute. Oops. So what I'm going to do is just kind of put a breakpoint in here and just see if and where, like how the collision detection is handled. So if I go uint32, I blah blah blah. So all I'm interested in is at the moment just to see, do we get in here, and one, do we get in here, and two, does it blow up? And which body do we get this data from? So we should be able to at least get the entity type from this and go through a switch statement. So yeah, yeah, that means you can't have entities without jolts. Oh, sorry, when I say I store them in Jolt, it's not like I have user data. It's like I refer them via a pointer that gets casted. What did I get here? Oh, right. Okay, so it's a weird. Oh, did I not? Why are you different? Excuse me for a moment. Oh, that's why. Classic mistake. So you should be... Thank you, linker error. That would have been annoying. Right, so... So the rock is not doing anything. So we have basically a pointer, JTAG, that points to some data. It's not stored in it, in the actual data structure itself, but we'll... I'm trying to avoid that, actually. So I'm just going to make sure everything's kind of valid. From what I can see, it is. We have the same code, it's just moved to a different place. And we assume we go through this first, so... Alright, let's just see if it blows up. It looks terrible. Okay, so get radius doesn't exist by the looks of things. Get collision shape. What's the issue here? Access violation on this pointer, maybe? Yes, this was null. So this object that was sent in was had nothing in it. Interesting. I assumed that when we pass these in, they're constructed. So I don't know why the object references that this pointer is busted up. Because we have this here, we pass it in. This comes through in... So the 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. And this is for what? This is for a get radius. Yes. Player. So it should be the first thing that's come through. Yes. I'm going to do a get radius. The data seems to be there. It doesn't seem crazy. These are default values as far as I remember. Strange. So we pass this in. It's a const. It's a const reference. So it should be good because this is also a const reference, as far as I can tell. Body. It's the same object type. Yep, same type. Okay. And this is passed in here as an object. What are you complaining about? Okay, I thought the playlist was... I think we need to move on to a different track because it's looping. Let's play one of my favorites. Quickly, wherever it is. Okay, never mind. I'm too high up in the playlist. Let's go Chrono Trigger. Not sure if this is relevant, but you can destruct a T from a T star with standard delete at. Okay. I don't think that's relevant, but that's good to know. I actually don't know that off the top of my head. I'm not familiar with construct at or delete at, which is kind of a new thing to me. Yeah. Okay. So let's get back into this and okay. We have a shape object and that's coming through here. Does it have a radius? That's the next thing. Set shape reference. Oh, I think I may know why this has happened. It's possible this has gone out of scope and we've got a dangling reference to the set shape object, which, let's have a look, which does stuff with, ignore all the squiggly lines. So there's a shared pointer thing happening here. I want to look at this. This is a... What is this? I thought this was a float. It is a float. Why would the this pointer of the shape sphere? Okay, so this is the... Okay, this is for the player though. Sorry, we're looking at the wrong thing. Okay, so build seed. Okay, as far as I remember though, when we have a function, we put something on the stack. We don't pop the stack when we go into a function. So why would it be a dangling reference? That would be in here, maybe. No, but even that's doing the same thing. Okay, let's just think. Okay, player is handled differently, actually. Look at this. Okay, so player is handled very differently. Okay, this is important. Player is handled differently. It looks like I haven't constructed enough data here. So when I pass this in... okay, so... Yeah, we need to do this. But I think when I initialize... Play... Okay, so this is not a dangling reference. It's just an unconstructed object. So that's what it is. It's an unconstructed object. I actually initialize the object that needs to be the collision sphere within our guy down here. But the problem is, do we need this anywhere else? No. the order matters here. What I could do is this, and then do this cast again, just for like this, and settings, player settings, right? That's not it. Now what goes in here? This might be too kind of convoluted, I think. Character settings. Where's the player settings shape? So I definitely wrote this when I was tired. That's all I can tell you. I see. Okay, so it's doing a bunch of stuff that I don't want to do the way it's doing it. Okay, so I definitely don't like this anymore. So it owns its own object. Okay, so that breaks the pattern completely. What do we need to use this for? So yeah, this just basically duplicates code if this ends up happening. So what I'm going to do is... Okay, so it can have its own character, but I don't think it can have its own body settings. What I'm going to do is take this out. Yeah, because this is just going to be duplicated code if I leave this in. Now ignore that for a minute because I can just send that in as an object, but what I'm going to try and do is, if I go back to my scene code, get rid of this, and I'll go to settings, shape settings. And if I want a different shape settings, I think it's going to be okay for now at least. Oh, come on, Intelligence, work with me. There we go. So I'm going to grab this, put this here for a minute. Move this up here. I don't know what's the air quotes best thing to do, but you know, you can't modify an object, so I'm going to actually move this out. Yeah, if this is all following the same idea, then this needs to be here. Oops. Okay, so the player, it's going to have less data in it now. So I'm going to steal this. So it needs both. Okay, if we're going to have that scattered around. Okay, so you may not like what I'm doing here, but what I'm trying to do is restore it back to normal and then kind of do something a bit more sane. Because clearly I've done something insane when I coded this originally. This is the problem with coding at the end of the live streams when I'm really tired. I'm going to start making silly mistakes. So I'm glad I've decided to do this because I've found a bunch of silliness. Yeah, so what was this originally? It's just a vector? I assume this is just 0, 0, 0. So right, let's construct this to 0. Okay, so at least I'll have the shape constructed. Right, next is to worry about the player object itself, which is a lot lighter now. Yeah. I'm just making sure everything's good in here, that I don't have any weirdness. Okay, so we need player shape to be constructed with a reference and the model. So there's 2 extra arguments now. And I think at the very least this is a bit more the way it's constructed at the moment anyway. Every object has its shape constructed before its entity is built. Again, it's a bit overloaded, but whatever I did before was even worse. So right, so I want to give the player its shape. Why do I need to do that? So let's think about this. Problem is if it's just here on the stack. Can I get some water, guys? I have not really planned this day very well. I haven't got my lunch ready and I haven't got any water, so I'm just gonna grab some water. So yeah, bear with me just for a moment. Just scroll in. And we'll keep on attacking this. Yeah. Be right back. Get my water bottle filled. The clicking noise is back from our water bottle, so my throat doesn't get super dry and sore. Okay, so we need the player reference for the character object, and whoops, I'm not saving that. We don't need BRB for later. Okay. It's better. Always hydrate yourself when you're doing this type of stuff. Okay, so what do we need to do then? Player settings. That needs to, does it have anything in here that's useful that I can send over? Because it would be nice to get the I wonder if instead of sending over another argument in this already overloaded function, we could just construct the player with the stuff it needs and then use the settings object. Oops, not that. I'm in rock anyway. I need player. So player needs 2 things. It needs, let's have a look. It needs M shape, which is great. But I think it's called something else if I use a, I think it's got a type def. It is a yes, this thing. Yo, Kingdom Hearts. Good pick, playlist. Did anyone play this game, Kingdom Hearts 1, and just like spend like basically 100 hours like on Destiny Island trying to grind for no reason? I feel like I was the only one that ever did that. Like I was like, oh, I've got to be prepared, so I've got to I've got to be on this island forever, killing Waka over and over again. You never know what boss will come, and then you absolutely steamroll the game because you're over leveled. Okay, so what else we need? We need What are you? Oh no, go back. Right, so, and what does this need to be? This needs to be a, okay, so a const jph mat it's arg. I can't remember which way around it is. Arg. Shape model. Should be model shape really, because that's how English works. Model shape. Right. Okay. So let's throw this in, and you know, I feel like listening to. Hopefully, you guys don't mind the complete Kingdom Hearts soundtrack. Let's do that. Complete. Hopefully it's not the. No, I'm kind of nervous about Square Enix right now. Actually, I don't want the whole live stream to be muted because of that one thing that I decided to put on. So we'll just be a bit more variety focused. Because I don't know what the deal is at the moment. Okay, so it just needs to be a normal map for. Oh no, wait. Are we modifying the object? Is that what it is? So it can't be const. Should have just checked. Ugh, come on. Qualifier dropped in binding reference of type. What? Okay, so yeah, it must be const. But why is this const? Why is this not const? Does it have to be const? I don't do anything with this object. I just read data. Yeah. Yeah, I don't know what that was about. I don't know why I made that const, but there we are. Okay, I'll put that as map 4. Now I've changed it and can't be bothered changing it again. Okay, so we have everything we need for player. Let's go back to our scene. Let's not open physics again. Alright. So, on initialization of player, which is this thing, we need the shape. I hope I can just get this. Shape. Get shape or something. If not, I might even modify the source code. But I think it's better written than that. This thing. So I need shape. Where's the shape itself? Get shape. Yeah, there it is. Why is it? What? Oh, that's the. Let's have a look. Okay, so we have a bunch of stuff going on here. If M shape is equal to null, which is the reference thing. What is it returning? What is this? Wait a minute, do I even need the shape reference? Hang on. What do I use this for? Oh, it is. Ugh. It's more awkward. Yeah, so const ref shape type. This is tricky. I don't want to just send over the reference type. But really what I need to do is... Oh, yeah, that, but that's private. And where is it? Can I access this anyway? Let's go to here, just see if it's used. Nope. I want to go to the CPP file because there's a bunch of stuff in here. Convert shape setting. Can I access? Oh, it's right there. Fantastic. So get shape returns shape pointer. So we'll try this and we'll see if the simplistic cast or whatever is whatever it's doing is allowing me to do that. Okay. Cool. That was a bit weird, but wait, are we passing the shape? What do we need in this in the third argument? Oh, the actual model shape. So this fella, I was going to say. And let's go in here and see if this is all happy. So I really do hope that this does a normal reference counted thing that it needs to do. And not just something else. Okay, so that's generally the cleanup that I've done. Reduced a bunch of code. I've moved basically the initialization of the player to here when it comes to its shape object. I know this isn't the most ideal code, but let's move this as well. This is kind of tricky. But I'll find a way to build the scenes, build the actual objects a bit better another time, I think. Because we are repeating ourselves quite a lot. And it probably would be nice to, say, build duck, and it kind of does this by itself. And then, you know, build other things. But anyway, so that should have got rid of that error and hopefully cleaned up a bunch of code and reduced the amount of lines. Okay, let's see. Let's see what I broke, eh? Let's see what we broke. Alright, cool. I was going to say, that was a bit of a longer time to boot. Okay, so it's actually more... Let's see if this still works, eh? Huh. What is... Okay, so have I got rid of the noise or something? Oh, I did, yeah, I removed it completely. But we should be breaking on a entity type. So the reason that confused me was I actually got rid of the noise. I didn't realize. Let's bring that back because that actually is useful. Oops, nope. Alright, fine. We'll just we're not release, are we? No, I just wanna okay. Okay. There we go. Rock. So it's probably some setup code stuff that I haven't done, but we'll see. And now we just want to sometimes the compilers can do stuff weird if you don't use the variable. It's like an unused variable. That still will get optimized out with 03, but hopefully debug doesn't do anything with it. But yeah, we'll see how this works. Yeah, at the very least, we've cleaned up the creation of entities code, which was getting terrible. This is kind of weird, though, that how long that takes. I don't know why it takes longer all of a sudden. Why are you so jussery? No sound either. Interesting. So when I crash into this... Excuse me. Unless it's doing a different audio or something? Warning. Validation settings. Oh, what? What's the audio interface? So this is one, taking longer to run, and two, not doing anything. You initialize thousands of what feels like, yeah, thousands of size 4. Ah, I know why this is taking so long now. Yep, I know why. I know why. And I can easily speed this up. And I'm going to try to do that. I know why it's going slow, but I don't know exactly why. So player, and let's get rid of this for a minute. How do we know what type it is? Oh, I'm not setting the type, I don't think. Well, that will do it. Okay, so player entity type equals yeah, so that was the mistake I was making, but I'm also making another mistake which I want to fix as well. Player, and that is what I was doing earlier, which I don't want to do. I don't want to initialize tons of tiny little objects if I'm never going to use them, and I'm going to try and get around using them because it's going to be so there we go. That should be, the physics engine should speed up now. We should, because we're not initializing thousands of little tiny bits of data. Cool. We're still getting that jusseriness, but one step at a time. Now we should at least get the crashing noise or and a breakpoint. I don't know what that's going to sound like. Hopefully it doesn't do something horrible. No, interesting. Okay. Let's see. Okay, so our user type is set. Is it unset? Yes, it is. Okay. Yeah, it was unset by something. Yeah, I've got to make sure that my duplicated code is an overriding code. Yeah, let's crash into this. Nope. Okay. But still, that was a progression in the right direction. So we do have entity type here and here. Now I see that technically should work. Yeah. Okay, so when we do the collision detection, are we really getting nothing at all happening? I'm kind of curious now. We should be getting at least something come through, because it's like, this is the whole point of this collision detection, right? So, crash. No. Okay, so this is not even ran. Because this is always 0. I'm just going to check this function even runs. Yep. Okay, so it does some collisions initially. Because it's pushing out the objects that have collided into each other. And if I crash into this... Yeah, okay, so... but we get a 0. Alright, so let's see. So when we send in our types, we have 2 ducks and we have a rock type. Okay. Whew. This is not what I expected to struggle with, but we're good, we're good. Let me just check something real quick on the monitor. Okay, so what's happening here is we've got a weird problem where we end up doing a collision detection, right? Okay, ignore that for a minute. And all the data is coming through is null, which is weird. Because at the very least, one of these should be triggered. And if I crash into these. So let's crash into it again. And we should see that... Okay, so we've got 0 there, because obviously we've got the same behavior. But why have we got 2 bodies with the same data? So let's just make sure we are setting the data properly up. Okay, so in this code, we've got to make sure that the set user data is actually correct. And as far as I can tell, when you do, this is how you do it, right? I have a global instance of the physics engine, so I don't initialize anything twice. And I set user data based on the body ID. I can see my mistake. Body ID is empty. So, yeah. Let's correct that. That's a simple mistake of just things done out of order. So we can do that. And we should now have everything kind of working. It would have been nice to have a way to see. So let's actually do this again. Put breakpoints here and here. And there we okay, so the player crashed into something. That was my yeah, there we go. Okay, so it's done the rock. We have the thing. Fantastic. So at the very least now we can delete something, right? Because we have a way of dealing with sorry, one moment. We can now extrapolate out this because we cast this to an entity, right? So we let's look at this again. So we have this thing bolded up here. What I want to do is use that to delete something in the array of things, right? So that's my method. That's my crazy method of what I'm going to try and do today. Okay, so let's go back. Let's get some more water and think about what we're going to do. So now the scene creation code is working. We can effectively, what I'm going to do is if current entity is entity index. Okay, there we go. Uint day2 for a minute. I know this is not how we're going to do this, but let's go to the I as well. To delete equals. Okay, so this is the idea, right? And it doesn't matter which one it is. We need to be able to take this guy out and do some deletion code on the entity list, effectively the array of fellas that we've got, and that exists in our, unfortunately these objects are not, they can't see each other's data right now, but that's the next step. So effectively, my next step is getting this arrow to connect, right? So we have the object, but at the moment, we effectively don't have this arrow. We have the idea, but we don't have the connection. So that's the next step, getting this to connect to that. And hopefully, with get user data, deleting an entity thingy, it won't cause a horrendous race condition. I hope not, because this is not in the Jolt physics engine itself, but we're gonna have to find out one way or another. Okie dokie. Right, how do I want to do this then? So let's look at our code again and figure out exactly what needs to be fixed. Sorry, what needs to be connected to what. So our scene, I think, has the actual stuff in. So I want to delete something out of this. Effectively, I have a crappy deletion. I keep going to the wrong file. So in game, I have a really terrible way of deleting code. We reconstruct a buffer from scratch and we delete something from an array, which works kind of. But I now need to effectively get in here with our entity index from this, which is just kind of like a general physics. I love this song. Okay, so what I'm trying to do is we're trying to get this guy to get into these two. So I need this to come here, right? And how many objects do we have? We have, so my contact listener is an example listener. And once this has been filled with a value, we need to then do something. What we could do is, I don't know how efficient this is, but as far as I can tell, if we're doing things in sequence and we don't have any threading, we could just say delete one thing per frame, which is probably not very good. We need to like delete things before the render rather than in sequence, one after another. So if we have like 70 things to delete, we need to delete them all before we render anything. Otherwise it'll get confusing. Right, so I need to think. I feel like we need an array of things to be deleted, like a deletion, like a queue, and use it as a stack effectively. If there's something in the stack, then we need to delete things, and then once we've deleted something, we then pop everything off and then skip over everything once it's empty. So what I'm saying there is, unless someone shouts at me and says no, we effectively need another data structure to store the data in. So in here, we want to push back things on a stack of entity indices that need to be deleted, and based on that alone, we want to so for example, we have, let's just write it here quickly. We have uint32 to delete q, and I'm not going to initialize it because I'm not going to use it here, but basically we push every single time we wanted to delete something. And then we say basically if this will be in the actual update code. In the update loop, we want to go and say is to delete q dot empty. Hang on, size not equal to 0. I guess I could say, or greater than 0. I can do maths. If that's the case, then we loop through all the. So yeah, I'm just going to type out the code here and work backwards then. I is equal to. Okay, so that's the idea anyway. And to delete. At the end, we pop. And in here, then we go into this. And the equivalent of... I'm going to copy some code out that we're probably going to deal with a bit differently. So we shall see. Yeah, so all this and the instance count stuff, which is kind of scuffed, I am aware, but oh, and the body ID, I guess, which we can get from. Okay, we'll just copy all this out because this is doing a bit more than just. It's also like doing a bit of safety checking, which is so that's right, but instead of getting the to delete Q, we do kind of like this system. And then we say, I'll just say element for now because that's what it's called. In everything else, so ignore the .c not working. But effectively that's the idea, and here we don't need... Yeah, we don't need element's going to refer to itself here. So we don't need this, really. We're just going to use elements because they're going to be the same, I think. Okay, let's assume this works. The delete queue will have... Is that going to be correct? Excuse me. We'd also need to know what type it is, I think. So rock, maybe. We need to. Okay, yeah, let's work through the deletion routine, and then we can figure out how to connect it. So now we are working on the actual this thing. Okay, so that I was going to worry about the connection. So technically, the only thing we have at the moment in our we only have this arrow. So the two things we need to make are this and this. So they're effectively disconnected right now. Oh dear, give me a stretch. Oh, but let's have some tea later. Got Get some caffeine in my bloodstream. Yeah, I stayed up to like 11 o'clock last night. Not the wisest move. Let me get some more water. My throat's quite dry today. Alright. What have we got? We have... So we need... Okay, so there's a couple of things we need to worry about here. We need to worry about... There's 3 things. Get the body ID from the entity index. Get the model type and debug sphere. Actually, you know what I need? I don't need... You know what I need? I need more the actual... I'm not gonna... Okay. I've changed my mind a little bit. So I think it's gonna be more beneficial because it needs more data than I realized. To instead of... We're just actually going to put the entity that we're going to delete in the array instead. So this will be entity. The reason I want to do that is because this has more data, even if it's a... Like, as far as I can tell, we have a pointer in here that's just not going to work. So with a shallow copy, with the default constructors, it's going to copy all this fine. But this is not going to work, the entity data stuff. So the only reason I'm doing it like this, I don't really need... Oh, what am I doing? What am I doing? What am I doing? No. Go back. I'll just come up with a better idea. So no, oops. We still need a deletion queue for this, but instead of doing, just a random element, because this entity index is a way to index into its own array, then we go, okay, scene dot entity, and then this would be not entities even, to delete. Yeah, to delete I. This should return an entity. Type. Sorry, entity. So again, this will not work with the void star because of the shallow copy. But I don't really care that much. So we have entity. Then we can basically do this. This is what we need to do now. This vastly simplifies things down. Because if I need an entity index or something, then it's going to be much easier. Okay, so I could do this and then be like, okay, index to delete equals this, and then delete these guys like this. Next would be to switch over the type. So instead of having this like if statement thing here, we're going to have something similar. We're going to have entity type. Yes, that's going to be good. So that's going to tell us the... Actually, what? Do we have anything else? We have model type, actually, which I think is what we actually care about instead. So we're going to grab, with our model entity, we're going to go over here, case, I'm going to paste this in, break. I don't think we're initializing anything. This is just to reduce the instance count draw call by 1, basically by whatever we need it to be. So this would be the duck model -1, and this would be for the, we need the rock model -1. So that's much easier to work out. And for now, this is the debug sphere. We don't really have a debug type, I don't think yet. Let's see. Yeah, I think we will in the future, but not now. So effectively, this is always going to be a -1 on the sphere. Okay, so now we can get rid of this bit, which is, you know, much nicer. Okay, so we have the index. In fact, we can move this like this further down where it's actually needed. Okay, so we got an extra safeguard there. And I'm not going to worry about this position being working right now. This is to do with something else. In the code base, I could just make this into a function. And that would make it nicer. Okay, so we have entity not equal to 0, 2 deletes. We delete them. Okay, so what is this doing? Oh, okay, so it's the... Yeah, it's this I need to do. Okay, so we just need stable IDs that are actually going to work properly. But for now, this will do. It's a bit naff, but yeah, we'll see. I wanted to actually get this far before we did anything substantial with our ECS type, well, our baby ECS. Okay, so let's think about this one more time. So we have we're gonna have a list of objects to be deleted, which I could just make public and make it accessible everywhere. Based on that, then we want to grab out the entity that we're going to deal with just to get the data, basically. This is just to get these two things out. And yeah, so I'm going to write a new piece of code, I think. This is going to be its own function. So I think it's going to be public here. So what I'm going to do is I'm just going to lazily throw this in the top of name space. So we're going to have a bit of global statage, but that's fine. And we need to initialize this, otherwise it can never be used. Maybe it would actually be better just for thread-based things. So this is assuming that we don't have any race conditions, but I need to write it out first before we can do that. Worry about that. No, it needs to be global. Okay, never mind. The reason is... Alright, so... go to game. Now, so let's put this in physics. Physics.initialize, which is fair enough. We only do this once anyway. Int it. Oh, that's a play a cool track then. Boom, boom, boom. Do we have memory service in here? Yes. Memory service. And we're going to go with instance. And let's do it with system allocator. And we're going to make this 4 because it's going to be very small. And let's put this back. Put this in here. Like that, so it doesn't get leaked. And then every time we delete something now in our guy, we have a connection. We're effectively building this arrow up. We want to dot push back. And then I think after, even if this doesn't work, what I'm going to do, I think I'm going to start transitioning to the book, okay? Because it is important I continue with that. So we're going back to book club study time after this, which is to do with the physics, which is the title of the stream. Okay, so we got rid of this. Now we need to pull this out into a whoops, a daisy. Okay, thank you. Hate it when I do that. The right stream for when I'm sad. I hope you're not sad right now, but if you are, I hope I can cheer you up at least with my terrible coding skills / studying some crazy esoteric maths for crazy ray tracing. Right, but it's good to see you empty code. I haven't seen you before. Okay, so we're going to have a void delete entity function because I'm sick of writing everything in the loop function. Right, so let's void delete entity. Right, cool. Now I'm going to throw in all our code, which should be easier to access if it's because this is the same object where everything lives. And effectively, we have game. Again, this isn't the ideal place to put it, but for now it's going to be able to access all the data it needs. So what are we interested in here? We want to put this. I'm going to get rid of some code as well, just to clean things up a little bit. So we need. What do we need? There is a deletion code stuff that I want to remove, which is where this has all come from. This. Okay, so we're not going to have this deletion by 0 anymore because this is just scruff. Leaving that around. Scruff central. Okay, fantastic. Let's. So this is still the update section of the code base. We have one big. I think I might split up my loop into 3 functions eventually. Just because it's like loop is a bit big, and it's the demarcation between the updating the physics, the handling the input, and drawing the actual things is a bit. It's all just kind of like vibes based at this point. There's no like clear line between the two. So if to delete. Okay, so let's see. To delete. Oops. Do delete q is size. Oops, come on. Is greater than. Yeah, so if it's greater than 0, then delete. Aren't you studying today? I will be soon. This is the end. I wanted to do a bit of coding just to keep my skills sharp on the coding side of things. But yes, we will be studying shortly. The title of the live stream will be true in a minute. I kind of overran a little bit, to be honest, because I wanted to at least get kind of this kind of all together, where we have the jolt physics getting an entity index that then does a to delete on the rows at the entities. I kind of want to have this going on here, and even if it doesn't work, I'm going to at least so we're going to grab my version, which I improved. Oh no, I want to grab cut and throw this in. It probably won't work, so that's going to be complete. That's I think I've got a bit of a self-fulfilling prophecy heading my way. Okay, so oh no, I did copy and paste it over. Nice. Yeah, okay, fantastic. What is this error? Okay, that's just a leftover. And we are deleting everything, blah blah blah, very nice. And delete entity if this deletion queue is greater than thingy. Okay, so let's just see what happens, right? Is the entity from an ECS? No, I'm not using an ECS. I'm using something similar. I'm using like a smaller clear enough heights. Hang on. Yes, you're right. This should be J. That's important. That would break everything. So yes, I am. It's a very simplified, a very simple version of an ECS, right? And that's by design because I don't want to overcomplicate everything. An entity should just have an entity should contain. Sorry, an entity is just something that contains data and runs a function. That's how simple I want to think about it. So. I can simplify this again. Yeah, I could just do this. And I don't need to have this switch statement at all. Because we have a table. Alright, cool. Done that. Simplify, simplify, simplify. Right, so hopefully we don't have anything broke. Oh, hang on. It's gonna. Oops. Sorry about your ears there. So let's see how it handles colliding and deleting and stuff. Okay, so it's trying to do something, but it didn't quite work. Let's just see if it runs the actual code at the very least. So I want to see the arrow connection is working. So no. Okay, that's fine. As far as I can tell, that means we're not adding anything to this queue. And that might be because we're not pushing back anything. No, we are. Okay. Did these ever get hit? That's a bit of debugging before we continue on. Here we go. Crashing into a rock. Okay, so it does get added to a queue. What? Why has it grown so fast? Anyway. Okay, so it's going to go and do a bunch of stuff. So it's possible that when we get to here, size is 0. Okay, so there's some kind of miscommunication here. I can make this part of the physics object, which I might do. I don't think this global state is working for us. How many threads is Jolt using? It's using, how many is it using? Actually, good question. Last time I remember it's using lots. Yeah, it's using the maximum hardware suggested. Assuming that this returns less than If it returns 0, then this whole thing breaks. But yeah, it's using basically every thread available that isn't the render thread, which is why we do a -1. This is just, again, demo code. We don't have a scheduler, so we're just kind of throwing everything at the wall when it comes to our threads. All right, so I'm going to leave this here, and we're going to start studying our lighting. It won't be, no. But I kind of want to get it kind of doing something first. It's currently not even running, so this might not be thread safe. This might need to be thread safe. Sorry, I actually don't know yet. But yes, we're gonna what we're gonna do for now is we're gonna move on because we've been coding for 2 hours, which is good. But I kind of more important, but my what is it called? My plan really is to dive as deep as I can into the book, this thing. Now, I want to talk about this book briefly, just for a minute. So I'm going to pause that while I yap. So, well, yeah, we're moving into study time. I've done enough coding for now. So what I'm going to do, for those who don't know, this is a book on physically based rendering. Let's just give you a little introduction, and I'm currently typing up a bunch of Monte Carlo notes, which is extremely maths based at the moment. Okay, so I did a little bit extra last night, but I was so tired after not getting a good night's sleep that I couldn't do much. So this is the way I'm going to be doing stuff, though. So we're actually going to be doing what's in the stream, title and thumbnail. And we are currently on improving efficiency still. Let's scroll down to the bottom, which is roughly where we are. So we're about here. Okay, so let's make it a bit bigger. I don't want to talk about this book because I've been saying in the last stream, just briefly, that this book, physicallybasedrendering.org, this free book, is chapter 1 and 2 are a bit of a casual filter when it comes to its maths. But someone who's better at maths than me, because I'm not a mathematician, I all the maths I know I've learnt after school for a long. I don't want to get. It's a bit of a long story, but I basically didn't learn anything in school really. Well, in retro, I learned the basics obviously, but when it comes to maths, holy, I didn't learn anything for a long string of reasons. But okay, so I'm. That's just to say I'm not as experienced when it comes to maths, right? But someone who is more experienced with maths, looked over the code, over the maths in this book, and was like, "Bro, this is like poorly explained," and I kind of like got disheartened yesterday. I was like, "Oh, okay." So not only is this book really difficult, it's also poorly explained maths. But here's the thing, right? When you're trying to get better in general, not just as a software engineer, sometimes the universe kind of throws you curveballs. And despite this maths being poorly explained, according to him, who's good at maths, I think it's worthwhile fighting through this book. Because almost more for character development than the actual content of the book. And at the end of this stream, by the way, we will review what we learned. So, or at least try to anyway. I might even do it off stream. I might just read the book for the rest of the stream. But anyway, that's what I've been talking about. It's very easy to get disheartened when people better than you are like, why this resource is rubbish? You're doing everything wrong. Type deal. But anyway, so yeah, this is just to fill you guys in. Now I've mentioned that. So this chapter of this book, at least, the Monte Carlo integration, is because this book is meant for both offline and online, real-time and offline rendering. This is an offline rendered image, for example. This would be extremely slow to actually appear in the game. This is a not a photograph. There is so much like ray tracing talk in this that we're gonna have to try and plow through. So yeah, it's that's what we're doing here. We're trying to figure out how rays work, and I might even add ray tracing to the game. By the way, I really care about this stuff like afterwards, but to get to this point, maybe not sampling theory, but this is the more interesting stuff for me. I've got to go through ray tracing stuff. Yeah, so I like that. Making the book understandable was an exercise for the reader. That's funny. A cinematic, 25 seconds per frame. We'll see if it gets that far. I've also found a good resource that I'm probably going to implement off stream, just so people. I said this earlier in the stream, but it was a couple of hours ago. But I might end up implementing this ray tracer that Casey Moritori, Molly Rocket, if you're familiar with that guy, has written. And he has written it. I'll just open it up. He has written a ray tracer with SIMD and AVX and with multi-threading. So this book has a mathematically correct, if that makes sense, ray tracer. Like it's really good on the maths. I have a feeling that Casey hasn't done that, but he's optimized the actual software, whereas this book's optimized the mathematics. And it would be cool to kind of like see if I could combine the two. And see what ends up happening. But that's for CPU based ray tracing. I don't know if I'll end up doing that. I probably won't do that on stream because that'll be kind of tiresome, I think, listening to a live stream. Because these videos are like at least an hour long, and but yeah, it's all to learn, you know, physically, but to get physically accurate lighting. That's the whole point. I doubt you'll do spectral rendering too. Yes, with these BSDF, all that kind of stuff. So yes, it's going to be. I might not finish this book. I have a feeling. Sorry to keep talking about this book. I have a feeling that it's going to be useful up until a point, and then when I get down to here, like this stuff, all these type of things like wavefront rendering on the GPU, which seems to be path tracing implementation on the GPU that doesn't use RT hardware, ray tracing hardware, if that's what I meant there. So it might be, I don't know. I'm kind of like not losing faith in this book, but I feel like it's more. I don't know how to describe this, but I don't know how relevant like building the texturing code, like learning how the partial derivatives work in sampling over textures is going to be, like how useful that's going to be. The reason that that's not that useful is because that's what the fragment shader does for you. Well, the GPU does on the fragment shader when you're doing raster graphics. That's what these small deltas are. So there's a couple of things like that I might not. I might I might not continue with this book all the way through. Because at some point I think it's starting to get into purely offline rendering, because you would need to do texturing differently if you're doing offline rendering completely. So yeah, that's what I've been thinking about. Yeah, with wavelengths and RGB. I know what you mean. There's we don't need to do spectral. So what Ratchet's talking about in chat there is I don't need to simulate light bouncing through a prism. You know, if you have a light bouncing through a prism, you get like the light splitting up into a rainbow because all the light spectrums like split up. And with spectral radiance, with spectral rendering, there we go. You have that included. The downside of that is it's way more expensive, and you only get like a cool effect that you can kind of fake in other ways. But if you want like actually like truly physically accurate lighting, which is true for like movies and stuff, then yes, you kind of do want that. Regardless, it's kind of I realized this book is, like I said, it's more of an offline render than anything. And yes, I could probably get like really deep into the PBR type deal. Let's just have a look through. I'm kind of curious actually, because I do want to understand the maths. And even the BSDF, I don't mind implementing. But the BSSDF, like, no, that's too complicated. And how to do hair and stuff like that. So yeah, it's kind of like a so there's a couple of things that I'm thinking about, right? So it might make less sense to continue all the way through this book. But regardless, I think it's what I'm going to try and fight through is at the very least get through the Monte Carlo stuff, which I think is going to be just kind of nice. I did tell you this book was focused on more offline path tracing. Yes, I was aware of that, but I expected a bit more when I was reading this book anyway. I was expecting more of a kind of like a kind of like a balance, like it does both. But there are chapters in this book that I just don't care about. I think one of them being this texturing stuff, like this. I likely won't care too much about the sampling, which is like how to sample better. Yeah, but the rest I'm like, this is gonna be good. This is gonna be good. Like the spectral radiance and colors. That's just gonna tell me how lights work. So I think I'm gonna speed run this as well. This is just gonna be a bunch of geometry. So yeah, that's what I'm thinking about with this book anyway. So it might not be something I go all the way through with, because it's kind of more for offline rendering than I realized. But you can only really know that once you've started, right? So in the meantime, I might try other things. I might I've got some other books that I'm gonna be reading. Sorry to talk about it so much, but I am trying to figure out exactly like how to become a better programmer on the fly. So there's likely going to be some garden paths that I end up going down that lead me nowhere. But I think what we're going to do at the very least is finish this Monte Carlo section, which is still pretty dense after improving efficiency. So we'll go through these. We'll speed through that and we'll read this. And that's probably where I'm going to end this book. Even though we've got like a nice reflectance model thing here. So I might do this. I might just do this section. I don't know yet. So what I might do is, I'm trying to figure this out on the fly, so please forgive me for being a bit sporadic. Yeah, what I'm going to do, I think, acceleration structures are going to be exclusive for offline rendering. Acceleration structures in Vulkan at runtime are, I think, completely different how you set them up and what you do with them. I think the theory is probably the same, but I could just learn the theory and apply it to an a real-time renderer. I keep saying online renderer. So shapes, I think, is to do with the actual bouncing of the rays themselves. based on based on the direction and stuff. I don't think that's going to be that relevant, because I think that's what the RT hardware is actually doing. I could be wrong, but if I was to do ray tracing, right, and I wanted to do it off a triangle mesh, then yeah, I think there's like hit-based shaders, non-hit-based shaders. And I think that's what they're primarily interested in. They're actually trying to figure out the intersection, which is done in hardware. The camera stuff, I don't think is going to be useful, even a little bit. That's going to be to do with simulating a real camera when it comes to like the lenses and the films. So that's what that's about. But this is going to be useful. That's just general lighting theory. This will be a nice revision on maths, and because I've already started this, I might as well just finish it. At least now I know what Monte Carlo is. So we're going to probably do this, take no notes here, take notes here, skip, 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 do the reflectance model thing, which is what I'm interested in, and that's it. The rest, I think, is skip everything else. Yeah, I don't see myself benefiting from doing any of this down here when it comes to I did it again. Rendering things. Yeah, so Ratchet is more familiar with me, familiar with actually doing ray tracing with actual RT hardware. So the hardware will do ray triangle intersections for you. So yeah, I don't need to know the actual maths. I mean, it's interesting, don't get me wrong. Yeah, even some of this is going to be a bit overkill, but it's still going to be useful to kind of know, at the very least, these three. So yeah, this might be overkill. Oh no, that's actually useful, the microfacet theory. So yeah, that's what we're gonna do. I hope that's okay. I don't know if people were here for the whole book, but yeah. I need to be smart with my time, and if I'm gonna read this book, it needs to be useful. So yeah, hopefully that's okay. So Ratchet has said the spec defines how the math works generally, but there's room for vendor-specific things. I see. So yeah, this would be good if I was going to work for NVIDIA on the ray tracing graphics driver. You know, then I would need to know everything. But I'm not planning on doing that. Regardless, yeah, I think it's nice to finish off what we started. Maybe it's a bit of a sunk cost fallacy happening here. So let me think about this a little longer, because I want to make sure I'm not going to fall for the sunk cost fallacy, to be honest. Because I'm almost tempted, now I've said that out loud, to skip these two chapters and kind of just forget it. Because these are very specific to, again, working out how Monte Carlo, the accuracy of Monte Carlo stuff. Why am I talking about this? Because it takes a long time to get through this. It's not like I'm sitting here and reading this from top to bottom like a novel, and just skipping over the stuff I don't understand. I'm really trying to dig into this and understand it, and because of that, it takes a long time to get through anything. So let me just think about this for a bit. But yeah, like I said, because I'm streaming so much, we're doing stuff on the fly. Wait, aren't you designing your own RT hardware? I'll link if you need something to read in the morning. But it's really not reading requirement. Yeah, thank you. Thank you, Ratchet. Yeah, if people do have resources, by the way, there is a Discord server you can join. Which is, you can probably see here. This is what this is. Yeah, so I appreciate that, Ratchet. So, yeah, so it looks like you have a nice part. Oops, part of the spec. Let me bring up my. Ah, this, right, yes. I think no, I haven't seen this before. Okay. So this is how Vulkan works with its ray tracing, which is probably going to be more beneficial than plowing through a bunch of offline rendering code. Again, okay, so for those who are new to code programming, and what am I talking about? I'll just introduce this idea a little nicer for you guys who are kind of like learning to do graphics. So I don't know who's new here. I know some people who are chatting in, who are in chat are not new. But for those who are new to graphics, there are two ways of doing real-time render. Well, there are two general ways of rendering now in the modern era. And that's ray tracing, or path tracing is more accurately described. And that is done for offline rendering. Typically, this is simulating the light beam that travels from the camera, and it bounces around all over the place, and it distributes its energy, lighting up things as it goes, and it loses energy as it moves along, and it goes all the way to a light source, right? Now, this is helpful in many different ways to physically simulate how the light bounces from the camera, because we don't care about anything that isn't hitting the camera. So that's why we fire the rays out of the camera. And that's the general idea, right? The problem is it's so expensive to do that, even if we simplify things down, that you have to come up with a bunch of maths techniques, and also it's very slow and all that kind of stuff, that we don't do that type of rendering for games. We do something called raster-based rendering, which is what we used to do. We've done this ever since the early 1970s, I think, where you're very familiar with this idea if you're not sure what I'm talking about, where we just use individual pixels, we figure out what they are, like this pixel right here, for example, in a shader, and we color that in based on data we fed in, and that happens in a row from, I don't know if it happens strictly right to left, because we don't have access to the rasterizer in Vulkan, but the rasterizer kind of fills in pixels from right to left, like, and then goes down and goes down like this. Now the downside of that is one, it's much faster because we don't have to simulate the light bouncing all over the place, but it's much slower. It's much harder to do physically accurate lighting because we're not simulating the light bouncing, right? So that's why we don't use you use path tracing, which is following the light beam all over the place in movies, and you use raster-based graphics in real-time rendering. So yeah, thank you for Ratchet for teaching me this actually. So I'll give him credit there. So that is what. So when we're talking about offline rendering, we're talking about path tracing. When we're talking about real-time rendering, we're talking about rastering. Now, recently with ray tracing hardware, we have got to a point where we can do some ray tracing, not all. Ray tracing, we can't do path tracing. I don't think full-on path tracing. We can do some techniques with the ray tracing hardware, but not all of them. There is a lot more techniques in here that this book will go into that the Vulkan this thing does not expose, because it's not ready. We're not that far advanced. So just switch to a voxel engine for nice ray acceleration structures. Can't be that difficult or limiting. I mean, honestly, that's an approach that people have taken, right? So yeah, that's the general idea, right? And this book I hoped would be more what it's actually titled. As you can see, it's literally titled "Physically Based Rendering." So I thought it'd be more. I thought it would be more into this stuff, but it's really just ray tracing. It's a ray tracing book, really. It should be ray tracing, offline ray tracing, physically based rendering. Almost that should be almost what the title is. But anyway, you can do real-time path tracing, but it's difficult but possible. Yeah, like I said, we are limited. We have to do a lot more things to get things to even close to 60 FPS. So yeah. So what I'm going to do, just because I don't want to fall for the sunk cost fallacy here, I'll finish this off, this one, because we're basically at the end. And we'll blast through this, we'll blast through this, and we'll blast through this, and that's it. I think I'm going to leave that book after that, because that's the things I need to know. And even then, it's going to be a bit tricky to figure out exactly what it's talking about with rays. But apart from that, I think we're going to be good, because I think it's mostly maths. This book, 80%, about 80% of this book is just pure maths. So I'm just going to make sure that yeah, okay, so it's basically teaching generally the same stuff. So just bear with me while I scroll through, just to make sure it's not completely doing something insane. Yeah, so it's got the Fresnel stuff in it, and then it's got the conductors, which is the metal. And then the dialectics. I don't mind learning BSDF, which is more complicated version of BRDF. Because that's going to be the future, I think. I think before too long, maybe in like 10 years or something, we're going to be moving from BRDF to BSDF eventually. I don't know. Assuming that hardware keeps getting better and better. But this will just be good to know. So more just good theory. But maybe, sorry, I keep kind of doubting myself here. I'm starting to think. I'm starting to change my mind again, because this is so we got microtacit theory. Sorry, I keep changing my mind. It's just there's so much to learn in this. Yeah. Yeah. So let me keep passing this, because this is important. I need to. Part of learning is learning what not to learn, as well as learning what to learn, if that makes sense. So hopefully that's okay. Yeah, that's true. People are not buying the hardware as much as they used to. They never said they were doing it in real time. They did mention real time every now and again, or raster-based visibility. So they aren't lying per se. They mentioned early on in chapter 2.1 that there is a time constraint that you're under, which is computation, whether it's 60 FPS or whatever. They were talking about like compute being unavailable, so you need to worry about speeding things up. But it didn't. Basically, it hasn't said this is purely for offline rendering. So they haven't like implied. I think it's implied if you know graphics, that this is purely because what I'm thinking honestly is, when it comes to, let me just get my notes up real quick. So it was interesting to learn all this, don't get me wrong. What might be more beneficial to me, honestly, is going through this. So this is a like actually going through this properly, like proper dive into this. rather than what I'm doing at the moment. Yeah, I'm starting to think that this is I don't know what this book is, to be honest. The Filament Project is part of something. I think it's an engine for Android, yeah. So this is like not as powerful as I'm accessing, but yeah, I've got to be careful with my sunk cost fallacy here. All right, so what I'm going to do then, I'm changing my mind again. Apologies. I think what I'm going to do is just go through this. I'm going to finish the tiny bit of code, tiny bit of the book that I've got left. So I've got like a half a chapter that I've written out in my notes. So I'm just going to basically go through this, which is the only bit I've got left. I'm going to leave the Russian roulette and splitting even. And I think Filament is going to have more of a raster-based approach to what I'm interested in, which is all this stuff. I have read some of this in the past, but yeah, I think this is generally more useful for raster-based graphics, and I can actually learn how to do this properly quickly, rather than having to learn how to do an offline ray tracer, then translate that to a. I mean, it's still got some decent maths in, so the stuff I have learned is not going to go to waste. But yeah, yeah, okay, yeah. That's what I'm thinking anyway. So yeah, thanks for bearing with me. I'm probably going to do that. I'll just finish. Before I continue though, I will read what everyone's been saying. How are you finding learning graphics programming and these techniques? Has been hard. Yeah, it's been kind of tough. It's been fun. A lot of what I'm having this problem with graphics programming. So just to Marco Martin, that I think beginners also struggle with. So maybe other people can relate who are like at my level. That you pick a resource that's not appropriate. You go into it for a while and you realize it's not appropriate. So funnily enough, Ratchet has so that's what I'm struggling with at the moment. It's not the actual techniques, it's finding good resources to actually sink my teeth into. So Ratchet in chat has mentioned something that it's important to note, that this is based for a Android phone, meaning that GPU hardware the techniques in here, when it says, oh, this is slow, we have to couch that in the, it's almost the opposite of this, where this is like two things that we're doing computation in this case that it's way too much work that we're going through to actually get accurate results here. But for this book, it's going to be the opposite. We're going to end up with this like, oh, be careful, this is expensive, and we don't actually need to care about it all. In fact, we can do more than what's considered slow, because I'm targeting GPU hardware. And hopefully then I can learn rain marching and then be able to do the lighting that I want to do. Okay, so Yap session is coming to a close after I finish the chat. So T888, TW8888, thank you for joining us. I was doing cryptography with compute shaders. Wow, interesting. And I was kind of got demotivated somehow. Stumbled across your channel and another guy named Thelemon, who is live streaming these sort of stuff. Kind of inspiring. I appreciate that, dude. I'm glad I can be inspiring. I always like to hear that. Sometimes I feel like I'm often being rambling too much or something like that. So it's very much appreciated. Thank you. Yeah. So I hope you get re-inspired with your cryptography when you're in your compute shaders. It sounds really interesting. So yes. So let's finish off what we were doing, and finish off this maths, and call it a day on this book, I think. All right. So, but like people have been saying as well, there's no wasted effort when it comes to learning. So if you end up in the same situation as me, where you've kind of learned something and you think, oh, you should have done something else, the fact that I've gone through all the maths and I've got better at maths is going to help me in all aspects of graphics programming. So there is that. Even if I don't end up using any of these power heuristic functions and the balance heuristic function. Okay, so they also try to use half precision in some places, but again, use full precision version. Okay, thank you for that. I will write that down as a quick note. So Ratchet has told me something I need to be careful of here. So don't follow them exactly. Don't worry too much when they say things are slow. You are targeting GPUs. You can also use full precision in the hardware. In the graphics. In the BRDF. Bidirectional reflectance distribution function. Look at that. Okay, not half. Okay, cool. Right, so like I said, let's finish this off. Let's finish off. Oops, not that. Let's finish off. Where is it? Our chapter on multi-sampling composition for offline ray tracing, and then we'll abandon offline ray tracing because we don't. I'll put all my notes in a nice section as well. So there's going to be an extra bit of before we move to filament. Anyway, so let me just read what I said. Okay, now with multi important sampling composition, which can further reduce variance. It's motivated by the fact that if all sampling distribution allocates some probability to the sampling region where the integrand value is small, it is often the case that the region, what am I saying? Where were we? So the observation, this observation led to the multi-sampling composition, which further reduces variance. It is motivated by the fact that if all sampling distributions allocate some probability to sampling regions where the integrand is small, it is often the case that the region of the integrand ends up being oversampled, leaving the region where the integrand is high undersampled. Okay, so let's sum that up a bit better. This leads the integrand to be undersampled where it's high and oversampled where it's low. Okay, so MIS, even I keep saying MSI, composition is based on the idea of sharpening one or more, but not all, the probability distribution for each. So one or more, but not all. For example, by adjusting them to have 0 probability in areas. I see. Where they had low probability. Okay. So since you can, with multi-importance sampling, have one or more probability distribution function. Oops. Probability distribution function be 0. But not all. Probability distribution. We can sharpen one or more, but not all. PDFs to 0. To have 0 probability. In areas they had low probability. Cool. A new sampling. A new sampling PDF P prime can be defined as, okay, nice. So we got, I think that's, I don't know what that is. I'm gonna guess epsilon because it's a small value, maybe. All right, so let's write this out. LaTeX. We're all familiar with this guy, LaTeX. All right, x equals frac. Itchy nose. All right, so we want max 0 p x. So, I just spelled epsilon. Ep. So I have no idea. That's not it, is it? It's I think it's got ph in it. All right, so LaTeX, Greek letters. I don't even know it's an epsilon, by the way. Ugh, man. No. For goodness sake, LaTeX. So we are looking for. Where is it? It's like a squiggly. Oh, it's small delta. Small delta. Oh, yeah. Okay, so yeah, it's funny. We're gonna have a. We're gonna go to filament in a minute, where everything's gonna be like super conservative. And this is like the opposite. Maximize, where it's maximizing everything. Oh no, we do need that. Oh, minus. Oh my goodness, keep pressing the wrong keys. Apologies. Delta. dx. Let's go. Okay. Where \delta is a fixed value. Okay, so this technique is especially easy to apply in cases of tabularized sampling distribution. This is easy to add for a tabularized sampling distribution. I don't know why I sang that. There we go. Getting carried away there. In section 12.5, which we don't ever read, it is good. It's a good effort for environment map sampling. This can be used to help with effective sampling environment map light sources. Fantastic. Okay, so that is where we're going to end that, and to cap this off, what I'm going to do is just kind of break up these into small notes so I can actually reread the, if I ever do want to come back to path tracing and figuring out how that works for real, I can, I think I will still keep revising this. I do, it is interesting, so I need to start here, but I think what I need to do is move on to something else. So regardless, this was interesting. Offline so I think I need just regular ray tracing, which actually has some of the same notes in, but it's, so I'm going to put this at the bottom actually. So this is a big index of stuff. So there's probably stuff in here that I would need to explicitly find, you know, how to do ray tracing in RT hardware to know what the differences are between, truly know the differences between offline and real-time ray tracing. But for now, I'll just say this is all just offline ray tracing because currently I can't distinguish between the two. So because I just don't know enough. Right, so this is all about stratum. So let's just see what we've got here. So we've got stratum, how to calculate a continuous function. Oh yeah, so that was really confusing. So let's try and break this up a bit. So we have a Monte Carlo estimator that distributed over stratums. And then it talks about the, okay, so what I'm going to do is need to leave the stratum. Okay, so I want to split this up a little bit so I see. So the true value would be the expected value of the stratum. This would be the variance. So I want to split this up a little bit and go, okay. Stratum or strata, yeah. Strata sampling So variance, because that's what we're calculating here. Variance in strata. I can't remember if the stratum, is the stratum the whole? So add all the strata together. Okay, stratum is the whole. Variance in stratum sampling. Okay, so that was just like a random bit of maths that I needed to know. So I'm going to take that out and kind of make this how to calculate a how to get the mean of a. This was so confusing when I was learning this. This is just pure maths. But because I've had to teach myself maths and I never learnt it in school really. I didn't know how to calculate the mean of a function over a continuous domain. So yeah, bit of an L on that one. Not knowing that, but I know it now. Graphics theory. And do I have maths? I've forgotten. Yes, I do. Okay, good. This isn't really graphics. This is just maths. I don't really need to have it. I don't know where to put it though. I will stick it in graphics theory though, because it is used there. Where all my maths has gone. Cool. On to the next. So now I can reference this when it comes to variance in sampling. Fantastic. Okay, so that was fine. I needed to. It was just too big. What is stratified sampling? So I need like an introduction to stratum, and then I need to work out the errors. So yeah, like I said, this is extremely important for me anyway, so I can review this later. Graphics theory, and this is, I'm going to change this to offline ray tracing because now we have two. We're going to have two ray tracing tags, and let's grab all the notes. Oh, no, it's too far. Okay, nice. And need the Monte Carlo estimator. So physically based rendering, Monte Carlo, and then the Monte Carlo estimator is there as a main note. We also need, and what I need now is all of, whoa, nope. Yeah, I'm excited to learn the filament book now. Now I've done this variance in stratum sampling, stratified sampling. Variance in stratified sampling. So I guess I got casual filtered out of this. I was saying yesterday this is a casual filter, right? So I guess I got filtered. L. No, I don't mind. Okay, so how much do I need to remove here? I removed too much. I need to remove that much. Fucked up how they did that. I know. Did you like that? It's terrible. I'll have to cry for days. Nah, that's fine. Or personally, never. I can never like Matt Barr ever again. So where's the mean? I think I should talk about mean in here, which is why I had to. Okay, so what I'm going to do, instead of highlighting, no, I will grab how to calculate the mean of a function. And we're going to throw this in here as like this. Go mean. Right. So now I can click on that. That'd be nice to click on. Physically, so it's the Monte Carlo. What is stratified? Thingamajiggy. And this is all good. Oh, yeah, need to do this, graphics theory, and ray tracing. So I'm going to do another chapter, because I need to grab these two. Make a new let's call this efficiency. Improving efficiency? I don't know. Okay, so yeah, there we go. Let's make it line up. Nice. Efficiency with efficiency sampling. Improving efficiency sampling. Yeah. Improving. Sorry, I'll put on the music in a minute. Efficiency. Sampling. Improving efficiency of sampling. It's a bit of a long subtitle, but ing. Cool. Right. Fantastic. And I'll just get the variance in there so I don't forget it. Nice. Okay. Let's get some music on. You know what I'm gonna do? Yep, be quiet, please. Let's pick. I've been enjoying this so much. Oops, not reading. Red Dead Redemption 2. Highlands. Lost T. How is it? This one. This is just like a really cool, chill thing. Okay, so fantastic. Right. Oh, that's a bit loud. Let's just check the audio. Okay, that's really loud for you guys. Let's turn that down. It's so difficult to get this right on the fly. There we go. That's perfect. Yeah, I want your hearing experience to be. Considering it's the most important part of the stream, got to make sure that you guys aren't getting blasted with some thing I've decided to put on. Right, okay, so this, variance and sampling, so they can connect to each other. Very nice. And where was this used, actually? Okay, variance. And we need the original note. Physically, Monte Carlo. Okay, cool. Okay, done that. Let's separate more of these guys out so I can read them in the future. problem is stratified sampling. Fantastic. I love small notes. Yeah, Cook torrents or torrents. I'm not exactly sure. What is it called? BRDF is coming up soon. Very exciting. Very exciting. So we need this in here. Connecting all my the problem with stratified sampling. So we need this and nope. And we need what is stratified? What is stratified sampling? Oh no, we already got that. Variance and stratified, blah de blah. Fantastic. And now we can do the source notes. Okay, so it shouldn't be as convoluted anymore because that was the complicated part, getting the variance kind of split up. Now I just need my graphics theory. Nice. Okay, so importance sampling. What is importance sampling? I assume. I hope I split this up. Yes. What is and I've just noticed that this needs to be changed. Importance. Oops. Sampling. Very cool. Alright, that should be good. Now I can actually make that into a note. Oops. And I need to fix that. Actually, I can fix it here. Do this. Oops. T even. Okay. And we want to grade this. And yep, we need the picture as well. Alright, I'll just grab the text. I can just delete that. Yep, we can just grab all that. Where is it gone? There. Okay, so the variance stuff is going to be completely separate because that was a completely different topic. Okay, how to calculate the mean? I don't think it comes up. Okay, get rid of this. And there we go. Graphics theory, ray tracing again. And I'm going to put this in my graphics theory section. Right. Right, so we go down here, and the problem with it, importance sampling. Yeah, because there is a problem with it. I hope this isn't multiple importance sampling. It shouldn't be. No. For goodness sake. Okay, let me. Oh, maybe I was right. Never mind. Sorry. I thought... Is this multiple importance sampling? That's single. This is... Okay, that's fine. I'm not that worried. Actually, now I think about it. Okay, got this twice, and import sampling, graphics theory. Yep, we got this open twice. Okay, that's going to be easier to deal with. Okay, yeah, okay, so paste, go to that note and make it official. I'm probably going to have to get some food shortly, but I'll finish this off before we do anything like that. So, go down here, and one shall come. Why did I write that and then not finish? Right, I'll come back to that. It's better that I just kind of get through this quickly, more than I polish everything. Otherwise, we'll never finish. Well, we will, but it'll just take too long. Physically, Monte Carlo, and this is going to connect to what is important sampling. And you need to connect back to that. I didn't connect you to the source node. Not very good. And cool. So we've got ray tracing, graphics theory. Oops. All right. Finally, we have how to solve multi-sample. Okay, how to solve. Yeah, we're getting there. Yeah, this was the biggest chapter that we went through yesterday. We went through all the multi-sampling stuff. Alright, I'm just going to copy that as well. Just so I can copy the source code. Okay, and now we need to connect these three together. And you. So you need to be copied 3 times. So to you. And I like to connect the early notes kind of together like this. And then later not do the rest like that. So don't worry, it's not going to be n to the power of notes that I create equals the amount of connections I need. Combinatoric style. Okay, done that. And power heuristics next. So we've got 2 left. We've got power heuristics and where's the balance heuristic? Oh, I've copied the balance heuristic. In here, which I didn't mean to do. So I'll just cut this out. Just lazy. So we don't have to do this. Okay, next, place that in there, then I can do that. Okay, so graphics theory again and ray tracing. Fantastic. And connect this to the source node. And connect this to the variance thing, which was the last thing. But not to everything else. So you need to be connected to the graphics theory below here. And the power heuristics function thingamajiggy. The power heuristics. The power heuristics. Function. And throw that in there. And then graphics theory, ray tracing once again. I'm going to change this to offline ray tracing because it's not really ray tracing in the way I care about. So once we've done this, once we've organized our notes. But yes, consider them as streaming stuff for longer this time. You know, I come back to this, but sometimes we're going to have to a lot, but consider I'm streaming so much, I need to do the less not less interesting. I find this interesting, but I don't know what to say. It's the important, but what would it be called? It would be called the grunt work. Yeah, I'm going to say grunt work. Like, we've got to do the grunt work. Single sampling model. Ray tracing, which is going to be changed to offline ray tracing. So we need the multi... So if we go to my graphics theory, we need quite a bit of knowledge here. Not the stratified stuff. Oh, I haven't put them in. So that's how to solve it. The problem. How to solve it. What else is there? Got the balance function. Oh yeah, what is important sampling? I don't think it's there. Oh no, it is. Okay, so we need these guys in our, because this is quite based on everything else. I'll connect the dots off stream, but for the most part, there's other stuff that needs to be connected, like expected value basics and stuff like that. But for this intents and purposes, as long as the general concepts are connected after transferring them over, then I will be generally happy. This was just the text, which is quite basic. It would just require a bunch of prerequisite knowledge. And the final one is, I don't like that multi-sampling. So nope. Is it multi or multiple? Give me a second. Oh yeah, it's multiple. Important sampling. Composition. So to it. This is the last one. Composition. So this requires basically all the knowledge of everything you've learned up to this point. Otherwise, nothing will make sense. Final note. So this is going to have a load of connections. And we should be good after that. I'm just going to basically change this to ray tracing. And Monte Carlo. And we're just going to grab a bunch of stuff. So we need all the stuff here, basically. And to connect to it, not just connect back, but out. Whoops. We need to grab this guy and put this at the top. Multi. What I don't want to do in this is to have circular ideally everything should be connected to everything over a whole network, if that makes sense. I should be able to get from everything to everything else, but for the most part I have to do that through the central nodes. But it is what it is. Okay, so that's everything I took on sampling efficiency. We didn't finish the chapter, but I think that's more than enough work on offline ray tracing. So I'm just going to open this up and change that to offline ray tracing. And yes, I'm happy with that. I hope. I mean, it's probably not all strictly offline ray tracing, all this, but it's mostly offline ray tracing. And our graphics theory is now down to this for raster. Sag. Okay. Right, what I need to do now is push this up to GitHub. If you really want to read my insane scratchings that I call notes, they are in a repository that's public called Obsidian Notes. You would need to point this Obsidian program at it. So I'm going to say finished with all my ray tracing, offline ray tracing note taking. Nice. Okay. I'll push that up so I can reference that on Linux and other computers. That's why I mostly do this. Just be careful that you don't wipe your own repository of notes if you're also using Obsidian. All right, filaments and food. So we are. I need to quickly make some food because I haven't actually made my pack lunch today for this stream. So unfortunately, that means what I could do, actually, now I think about it, is make my food but take you guys with me. So I can at least talk to you guys while we watch a video while I make my food. And then go silent or something. But I need something to like yap over. Oops, I shouldn't have closed that, never mind. So let's find something. I might do that then. Let's close Discworld and all that. Okay. Have you guys come across any cool vids about anything in particular you want to study? We have the resource channel. We've done this ray tracing thing, but I think I'm ray traced out at the moment. What have we got? So we got ray tracing, Vulkan triangle in 2 hours. We have some maths. I don't really have anything in mind, so yeah. We could watch the Mike Acton talk. I've at least seen that like 10 times now, so anything in particular that seems interesting? Mostly these articles. That was kind of not that interesting, I have to admit. Alright, so higher quality version of this. What is this? Let's have a look. Oh, okay. So Ratchet has shared this a while ago. What is this?
This works. Nice, great. Hi, I'm Hugo. I'm a PhD student in Ireland, and today
I'll pause that for a moment. So we are on 5 hours and 55, which is no more shader languages, compiling C++ to Vulkan Spiv. Interesting. Does that sound interesting, guys? We can watch some. Watch this lecture. I think it sounds good to me. Unless I don't want to watch stuff like this, which is just like tech news. But yeah, it's nothing that interesting apart from that. So yeah, I will do that. I will. Let's close this. I'm not really that interested. Okay, so what I'm gonna do is a bit experimental. I don't know if it's even possible. But I'm going to be listening to this video, I think, more than anything. And I'm going to change the audio. And hopefully I can take my microphone over to the kitchen, which is quite close by, because I'm in the kitchen. And I can hopefully make some food, rather than just leaving you here for like 10 minutes with no streamer. So let's turn this off for a minute and turn this up to about 70-ish, something like this. And I'm just going to play the beginning. Nope, where's it gone? There it is.
I'm going to tell you why you should consider abandoning chaining languages.
Okay, how's this?
Okay,
I will turn him up a bit.
First, what the heck are shading languages? They're domain-specific languages whose domain is writing graphics programs.
Okay, that
the
seems good to
scope
me.
can be stuff like materials, writing what. Today I'm going to. Nice, great.
Okay, let me just move my mic and see if this is even possible. So this is a scuffed. So I've got to be careful here, don't unplug my microphone. Oh dear. Okay, so far so good. Hopefully you're still okay. That's as far as I can go. So I'm going to put you there. Now how far can I walk? Okay, that's reasonable. Hopefully you guys can hear me. I'm behind the microphone. Oh, and I'm going to press play.
Hi, I'm Hugo. I'm a PhD student in Ireland, and today I'm going to tell you why you should consider abandoning chaining languages.
So what I'm just going to do, guys, is just make a quick
First, what the heck are shading languages?
stream with no
They're
visuals.
domain-specific languages whose domain is writing graphics programs. The scope can be stuff like materials, light calculations, and image filters. In the offline world, you have languages like the open shading language or the material definition language. And in the online world, or what we call real-time, you have languages like GLSL, which doesn't have a logo, HLSL, which has a logo now,
imagine?
and Slang, which has a very professional logo.
Online rendering, real-time rendering.
So, what's the purpose of shaders for real-time rendering? Well, conventionally, we have this pipeline for real-time graphics, and shaders were introduced to replace the stages that I outlined in yellow, whereas before this was just fixed function. We have vertex shaders for essentially performing coordinate transformation, and we have fragment shaders to decide the color of pixels covered by triangles.
Fantastic, right.
Since then, we've invented many more shader stages, and Vulkan can have a very complicated looking pipeline. So what characterizes shading languages? The most important thing is that they embrace single instruction multiple thread parallelism. So you write your program, it's one invocation, and then you just spawn more of them, quite a few more of them. So your shader is effectively a pure function, and it gets executed in a massively parallel fashion. Shaders, especially the two stages mentioned, they perform so-called streaming computations. So the pipeline provides them with data in some global variable that gets annotated, and the data gets passed back. And that means that historically these languages did without pointers. And finally, these languages have historically had a narrow scope because the first programmable hardware was not that programmable. And even if you could program it to do fancy things, the performance budget just wasn't there, so you had to keep your shaders small.
Interesting.
So we found out that GPUs are really good at parallel processing, and that can be used for things that are not graphics. And because of that, we have invented languages that are made for general purpose computation on a GPU. These languages are different because they're open-ended. They're not really domain-specific anymore. We don't have pipelines, inputs and outputs. Because you define your own data layout, you have to have full pointers and define your own buffers and do everything yourself. These languages also tend to support larger programs, maybe even production renderers. And they have things like real function calls, the ability to define complex data structures, the ability to have some sort of template and many higher level features. And they also tend to support unified CPU and GPU programming. So that's essentially sharing a code base between the GPU and the CPU aspects of your code, and sometimes full-blown heterogeneous programming. And that's done, with a single language, at least if you're talking about CUDA or SYCL. The unfortunate thing is there's no real true unified GPU programming API, sorry. So in this yellow circle, I have a few examples of APIs that operate with graphics pipelines. You have Metal, DirectX, Vulkan, and so these APIs, they get access to the hardware accelerated pipeline. They can do texture sampling. They have access to all the knobs. But then you have the red circle here, and that's languages that have access to C++ or some other rich language. And these languages, they have access to full-blown pointers. They can do function calls. They can do recursion. Wow. And you find things like CUDA, modern versions of OpenCL, and as well as SYCL. And then finally, there's a third circle. That's the cross-platform, and specifically like being an open standard. And in there, you find all the Kronos APIs, which also includes earlier versions of OpenCL. And these, I wouldn't really say they have full-blown access to C++ languages. They're kind of more like shading languages and how limited they are. So obviously, we'd like to be in the center of these three circles, but there's nothing there, right? That's enough.
That was funny.
Okay, so we want to see better GPU languages. We want to have graphics and compute within the same language. But Vulkan supports compute, yes, but you have to use shading languages. So Vulkan is a good starting point, but there's some work to be done. We would like to share our code between host and device. And our third criteria, and I'm going to have to explain what this is, we want to have an embedded language rather than an external language.
Embedded?
So what the heck does that mean? So an external domain-specific language, that's a language you create from scratch. It's its own thing. It's got its own grammar. It's got its own type system and its own compiler. every shading language I've described earlier, and really most of them, bar a few exceptions, they are external ESLs. They are languages that are fully independent. They might be inspired by C or C++ and share a lot of syntax, but they're essentially their own thing. An embedded domain-specific language is when you take a normal existing language, a general-purpose language, and you use the abstraction facilities of that language, such as your lambdas, your syntactic sugar, for you have your implicit, your operator overloading, all these features to sort of create a subset or a library within that language to express some domain-specific knowledge. Scala is a very popular language for domain-specific languages. We don't really use it in this industry, but it's a pretty good example. I can also mention NEDSL. I mean, I have to mention NEDSL, which is the project we have at Zarland to make domain-specific languages, and we can do fancy things like we have a path tracer that's written in this nice, pure textbook code called Rodent, and then it runs really well. And the question I'm asking here is, can we have graphics shader be an embedded domain-specific language in C++?
Huh.
Okay. So, what's an embedded shading language like? Well, really, it's just a library. You need things like small vectors and matrix math, and a few helper functions, and that's mostly what GLSL has. And then the rest of it is just plumbing, for lack of a better word.
Yeah.
We have these texture sampling operations here. These are just annotations on functions. These memory types here for the I/O annotations. The binding model for Vulkan, like these descriptor set things, believe it or not, it's way more annotations. And so we don't really need any new language constructs. We can just reuse existing C++ syntax. And these are not keywords, they're just macros defining this header here. So there's this thing called SPURV. I'm not going to complain about SPURV. SPURV is actually really great because before SPURV, you had an API, you had OpenGL, and then you had the OpenGL shading language. And that was the blessed language you had to use, and you provided OpenGL with a giant text string, and that was your shader, and OpenGL took it from there. SPURV is much nicer. It's essentially it's called an intermediate representation, which is a file format defined to be consumed by compilers. It's essentially like a sort of pseudo-assembly. And that's very nice because it means Vulkan can theoretically work with any language. The problem is that even though SPURV is used by both OpenCL and Vulkan, it doesn't actually have the same features depending on which language you're using. It's not unified. And there's this notion of a kernel dialect for OpenCL, which has access to things like nice pointers, function calls, and whatnot. And then you have the shader dialect, which is what Vulkan is bound to. And well, it's not great for us. Pointer usage is severely limited. We'll see a bit more on that. There's no generic address space, so every pointer has to refer to a specific address space. There's no such thing as just having T star, and that can be wherever. Yeah. There's no recursion. There's no function pointers. And like a lot of things are, there's a lot of extensions and quirks, and it's a quirky format, and it's not. If you're starting with a normal compiler representation like LLVM, and you're trying to go to SPURV, there's actually a lot of these things in the way. Okay, so what the heck are logical pointers? So in the shader.
Thank you for bearing with me on that. I'm just going to quickly eat my food while we watch the rest. I'm just going to move my mic back. Hopefully you didn't mind me doing that. I apologize for being a bit disorganized today. I hope I kind of got. I was a bit too excited to stream today, to be honest. I'm not gonna lie. I was like, oh yeah, let's go, and then didn't set up anything. I usually do. So I'm gonna meet, but because of that, I now. So you don't hear clattering of cutlery like I just did there, and chewing, which is probably the worst sound known to man. I am going to go and push to talk. We're going to watch this. This takes me about 50 minutes to about eat, and then we'll get back to studying. Hopefully that's chill with you guys, and then no more interruptions apart from going to the loo and things like that. So yeah, let's continue watching this local pointers thing.
dialect of SPURV, you have this notion of addressing mode, and shaders have to use the logical addressing mode. And what that means is if you have a pointer to something, if you have, say, a pointer to something, I have my struct S, I have a pointer to it, I can take my pointer to the struct and turn it into a pointer to an integer within that struct. That's fine, even though that's syntactically incorrect. But if I try to do something like access the next element in array contiguously, that is not okay, because that is not a sub-object of my initial object. And likewise, if I had a pointer to an int and I tried to upcast it to a pointer to an s, that's also not okay because it's not a sub-object. The second rule with logical pointers is that you cannot change the type you're pointing to. So if I have a pointer to int and I want to reinterpret it as a pointer to a float, that's not okay. And finally, pointers themselves are not first-class values. What that means is there's a lot of things you're just not allowed to do with pointers. For example, you can't pick between two pointers. With pure logical addressing, this is illegal. So if I have a Boolean here, and I want to pick between pointer A or B, not okay. And if I want to have a struct that contains a pointer, so if I want to store pointers in memory, that is also not okay. So you can't load and store pointers. That is extremely limiting. Your pointers are more like C++ references that you can't copy. It's extremely crippling. So, some solutions. The first thing is something called pointer canonization. So in our compiler, we sort of look at pointer expression and we try and make them all have the same shape. We try and put all the casts at the end and all the indexing at the start. So we try and get rid of any spurious casts we can avoid. We also support demoting. So if you have a pointer and we know it's representable with only these logical operations, we leave it as is. And otherwise, we emulate pointers with arrays. So that looks something like this. We have a big, for example, we have the private, like thread private memory. We're going to say, OK, we want 4 kilobytes of thread private memory. And all our individual allocations are going to be ranges within this array. And to load data and also data into this array, we just use offsets and we bitcast the individual values. So on load, we bitcast the value, and on source, we also bitcast it. So the array only deals with integers, but we can have whatever we want, and we can perform our casts, and stuff works. This looks and sounds really crude, and we benchmarked it, and it actually performs better than you'd think. Similarly, we have issues with function calls. As I said, they cannot be recursive. They don't. Functions don't have addresses, so a function is also not a first-class value that you can like store to memory or whatever. And in fact, you cannot call anything indirectly. You can only call functions if you say exactly which function you're calling. There's no such thing as function pointers. So the solution is less easy to explain. We do this thing called continuation passing style transformation, which will speak to some compiler nerds in the audience, but maybe not everyone. And what that leaves us with is code that only does tail calls. So there's never a normal call where we go to the stack and pop after that. We just always go to the next thing directly. It's just like only indirect go-to. And then we have a software scheduler to emulate, because the tail calls are still not allowed in SPURV. The software scheduler is something like this. We have a top-level loop, and the top-level loop has a bunch of indices. It receives an index, and this index is what function to run, or rather what continuation. And each of the continuations, because it's not allowed to do a tail call at the end, it just returns another index back to the dispatcher, which will call on to the next thing. And that lets us do pretty much arbitrary function calls and control flow within the bounds of the shader dialect of SPURV. Okay, cool. Okay, so what we've built here is a compiler. It's called the Vulkan.
That's really cool. Holy.
Vulkan Client Compiler, VCC. It lets you compile standard C++ to your shaders, and you can use it for any Vulkan shader stage. Theoretically, we haven't tried them all. It's based on an unmodified Clang front end, which is noteworthy because you don't want to be maintaining a fork of Clang somewhere. And we use this thing called the shady intermediate representation, which is essentially it's a SPURV-like thing we've made, but it's very tuned to the task of, okay, doing these array transformations, these logical pointers, dealing with them, optimizing them into something nice. As input languages, we support LLVMIR, which is how we make VCC happen. We invoke Clang, we tell it, okay, compile our thing, and then emit LLVMIR. We parse that, and then we turn it into what we need. We also support eating the kernel style Lisp-V from OpenCL, so if you want to go that way, that's also an option. And as outputs, we support shaders-V, so that's your nice Vulkan-compatible shaders. Also GLSL for fun. CUDA, because it's useful for evaluation, it gives us a reference. And also ISPC, because ISPC is a host language with debug symbols, so we can run our code and see what's going on. But it's still a vectorized, it's still a SIMD language, or a SIMD, right? So we can debug our code and figure out why it doesn't work, instead of just hanging the GPU and being stuck with it. Okay, so our headline application for this paper is we made a real-time path tracer with it. It's very conventional. It's a GPU path tracer written entirely in software. We don't use Vulkan acceleration structures. We didn't have the time. It does implement, therefore, a custom BVH. We do next event estimation. We have dielectric materials. It is not the fanciest thing, but it is a significant workload. It was written by someone who isn't a compiler author, my colleague Umechan, over there in the audience. Hi, Umechan. Great work. And that's significant as well, because usually these custom small languages, they're made by someone, and that someone writes software with it, and that's the only software that will ever work with it. And this path tracer can compile to both CPU and GPU, and we can even switch on the fly. So it's really a unified code base. We just have a header, and it goes, okay, if compiling with VCC, then use these intrinsics, otherwise include stud math and whatever. And we have the three scenes here. We have the corner box, we have the bedroom scene, and the dining room scene. Okay, let's look at some performance results in the same order as before. So for the corner box scene, and lower is better, we have the CUDA reference. Oh yeah, we have a CUDA reference, by the way. This path tracer also compiles to CUDA, of course. That's how we get a reference. And essentially, depending on the scene, so the corner box is the worst, and the other room scenes are pretty okay. We are between 0.5 to 1x the performance of CUDA, just straight up CUDA, which I would say it's not bad for a toy compiler made by a couple PhD students. It also happens to just work on AMD, on both the RADV and AMD VLK drivers. So portability, yay. And it mostly works on Intel and Apple through Molten VK. Anyone who deals with GPU stacks knows that it's a nightmare because there's bugs in everything, your software, but also their software. It can be made to work. There's no actual blocker. It's just we didn't spend the extra engineering time to make sure the path tracer fully runs on these platforms. It does run if you only run primary arrays. There's something wrong with the recursion. We'll get it. It's fine. We can also apply this to conventional graphics. That's our second application. We have written this really cute application with the fragment shader and a vertex and fragment shader. And it is a procedural terrain demo, which you've seen many times, this kind of thing on Shaders and elsewhere. We wrote it in GLSL as our reference, and then we just ported it. And I believe, I'll attempt this, I believe I can run it in real time. So this is the GLSL version. Yeah. Yeah, no, this is programmer art. It doesn't look brilliant. So we're running at what? Well, yeah, 120 FPS. That's different now on the projector. And if I run it with the shaders we compiled with VCC, it looks identical and performs identically. Oh, it's because I'm running on battery. Okay. I was getting 200 FPS before on both. You just have to trust me or check the paper. Or run it yourself. I'll get to that. Cool. So that's the demo passed us. So yeah, we pretty much saw identical performance no matter where we tried this thing. And the reason we figure the performance is identical is because we're not actually using any fancy feature that we have to emulate and do anything crazy. We just have a bunch of sine and cosines and Perlin noise stuff, and it's a known number of iterations, so the compiler can just unroll it into a big giant ball of math operations, and it looks the same no matter who generated the ball. The shader compiler just goes through it and makes it into something decent. Okay, so in conclusion, C++ for Vulkan, that's a viable thing. I think we have demonstrated that. All the code is available under MIT license on GitHub. You can scan this QR code to go to our website. The compiler, the applications, the benchmarks. I would propose the idea that shading is just a thing a language does. It's just a workload, a use case for a language. It's not a class of language, or at least it can be seen this way. We're very excited to see what can be done with this technology, both as for us as future work, but also for other projects. There's nothing C++ or Clang specific here. We just pass LLVMIR and then run this complicated transformation pipeline on it. You could just use this for your own language. I mean, Slang can use this, GLSL, if GLSL wants to be modern, they can use this. Zig, whatever, Rust, it's all possible. And yeah, I think there's a lot more we can do in the idea of unifying and simplifying GPU stacks by sort of moving on to more general purpose languages. Okay.
Have you guys ever used this before? This is the first time I've heard of it. Just pause that for a minute. It seems interesting. But I don't know how useful it is, if that makes sense. I've managed to eat everything, but I need to clean up briefly. Hopefully that's okay. I'll be back in like 2 seconds. I just need to move my plate and stuff so you don't hear clanging and rustling of things. And then we can get back on to our coding. Thank you for bearing with me, guys. I know it's not always the most fun viewing experience when I'm not here, but I appreciate you all, and I will be right back. So yeah, see you in a minute. Alright, officially back. No more distractions. Just gotta plug in my laptop because that chat is dying. Just make sure we're still live. That's the other thing, because I'm a bit nervous that I unplugged my microphone and no one can hear me. Streamer health, fantastic. Okay, cool. Okay. Fantastic. All right, let's dive into this, right? So, what I'm interested in is filament and more studying, so we're going to do that. So we need to make a new note. So we've got all the offline rendering done, which is half my graphics theory now. That's funny. Who would have guessed? All right, let's see. So we want to take, I'm going to call this an article, maybe? Article? Yeah, it's going to be reasonably dense, but it's not that difficult to get through this, I don't think. Unless these are individual chapters that are... No, okay, so obviously this is going to take a long time to get through. I don't think... What I'm interested in, looking at this, is mostly Chapter 4. That is the most important for me, and Chapter 5 probably. Chapter 5, and it gets less important but still useful. as we go on. So we probably won't need to go all the way through the end before we start implementing stuff in our game. Just a basic overview of BRDF, of the BRDF that we're interested in anyway. There's many ones out there. It's probably the most useful. So yeah, hopefully you're all here for that as we continue to study lighting, which is all related to this. And we just have to be aware that some of the stuff is, what is it called? I think what I'm going to do is split up everything into big note. Yeah, okay, so I'll read this out loud. So yeah, I probably won't take notes up until material system. So we'll just read through all this. And yeah. Whoa, don't go any further. And I'll split up into individual bits. Okay, so let's make a new note. Now I'll do as a book. It is a book. So this is filaments. PBR, and let's call this materials, because that's where we're going to start with. Whoops, dash materials. Okay, and hash reference. Reference. Reference n. Okay, let's grab this and can I get a link to this? Fantastic, even better. But obviously I'm going to start with the overview and stuff. And I will, yeah, let's dive into it. Okay, so let's get a bit of water first. Okay, so this project is part of the filament project. To report errors in this document, please use the project tracker. Okie dokie. Authors are these two guys, Romain and Matthias. Very nice. Okay. Overview. The filament is a physically based renderer engine for Android. The goal of Filament is to offer a set of tools and APIs for Android developers that will enable them to create high quality 2D and 3D 2D, 3D rendering with ease. The goal of this document is to explain the equations and theory behind the material and lighting used in Filament. This document is intended as a reference for contributors to Filament or developers interested in the inner working of the engine. We will provide code snippets as needed. To make the relationship between theory and practice as clear as possible, the document is not intended as... to make the theory and practice as clear as possible. Oh, I didn't start my thingy. Excuse me one moment. And there we go. Oops. This document is not intended as a design document. It focuses solely on algorithms, and its content could be used to implement a PBR in any engine. However, this document explains why we chose specific algorithms and models over others. Okay. Unless noted otherwise, all 3D rendering presented in this document have been generated in engine, prototype, or production. Many of these 3D renderings were captured during early stages of filament development and don't reflect the final product. Okay. Seems good. Just checking something real quick. I thought someone. I thought I heard someone at the door. Okay. Principles. Real-time rendering is an active area. Excuse me. Of research. And there is a large number of equations and algorithms and implementations to choose from. For every single feature that needs to be implemented, the book rendering real-time shadows, for instance, is a 400-page summary of dozens of shadow rendering techniques. As such, we first define our goals, our principles, to follow Brent Burley's seminal paper on physically based shading at Disney. Before we can make informed decisions. Our primary goal, our real-time mobile performance. Our primary goal is to design and implement a rendering system able to perform efficiently on mobile platforms. The primary target will be OpenGL ES3X class GPUs. Quality. Our rendering system will emphasize overall picture quality. We will, however, accept quality compromises to support low and medium performance GPUs. If we can get around that, that'll be nice. Ease of use. Ours need to be able to iterate often and quickly on their assets, and our rendering system must allow them to do intuitively. We must therefore provide parameters that are easy to understand. For instance, no specular power. Hey Dimitri, how you doing, dude? Yeah, just reading a new book instead of the physically based rendering one. So we're just diving into a new book. Just finished lunch, so ready to do something that's a bit more approachable and easy to understand, honestly. It turns out the book that I was reading was pretty much never going to talk about real-time rendering stuff, despite it mentioning it early on as something that it would in chapter 2 when talking about compute and stuff. But yeah, that book is never going to be relevant. Well, it will be relevant. Some of the stuff I did learn is going to be relevant, like dealing with the rendering equation. But the further I looked into it, the more I realized that unless I'm going to work for NVIDIA with the programming my own ray tracer, or working on the ray tracing part of the graphics driver or something like that, I won't ever need all that knowledge. So we kind of cut it off kind of early, and we're going to Filament, which is an Android-based game engine, I believe, or is it just a renderer? An Android, yeah, a real-time renderer for Android, and we're just going to kind of go through that, and hopefully that'll get us up to speed with some of the things we need to know. So, do you have any questions on the matter? It seems like you already know how to add vertex, and colors and shit. Yeah, I can do those things. It's more I need to figure out, for those who are wondering, I need to accurately know how to do this properly. The bidirectional scattering and reflectance functions. That's actually what I need. I need to know microfacet theory. Why do I need to know this? Is so I can, actually write an accurate PBR. Renderer. But apart from that, what I don't need to know is how to efficiently is all the ray tracing specific stuff that I ended up learning, which is fine. But it's better to cut my losses now and learn something that's actually needed rather than spend forever on that and stick through it for no matter what. Sunk cost fallacy and all that, if you know what I mean. Anyway, for both artists and developers, our system will rely on a few parameters as possible to reduce trial and error and allow users to quickly master the materials. Okay, model. In addition, our contribution of parameter values should lead to physically plausible results. Physically plausible materials must be hard to create. Familiarity. Our system should use physical units everywhere possible. Distance in meters, centimeters, color in Kelvin, light units in lumens or candelas. I don't know. Flexibility. Physically based approach must not preclude non-realistic rendering. User interfaces, for instance, will need unlit materials. Yeah, so we can't make sense, I guess. Development size, while not directly related to the content of this document, it bears emphasizing our desire to keep the rendering library as small as possible. So many applications can bundle it without increasing the binary size to an undesirable size. Okay, so physically based rendering. We chose to adopt PBR for its benefits from an artist and production efficient standpoint, and because it is compatible with our goals. Physically based rendering is a rendering method that provides a more accurate representation of materials and how they interact with light when compared to traditional real-time models. The separation of materials and lighting at the core of PBR methods makes it easier to create realistic assets that look accurate in all lighting conditions. Yes. Okay, so the equations found throughout this document. Okay, so what do we want here? So let's just have a look. Do we need this? View unit vector, light incident unit vector, surface normal vector, half between. Okay, so that's the H, the BRDF. Diffuse components, reflectance components. Okay, so roughness mapping from. I'm going to say that it's going to be useful, I think, to have this as a reference, but I don't know how to reference it. So when I copy this out, what do I get? Yes. No, you. I read that chat glass. Oh yeah, we were messing about earlier. About object-oriented programming. It was fine. We were making jokes. How do I get the LaTeX out? It doesn't really matter. I can type this out myself. I know how to do it. Except for that, though. Okay, so if I want to... Oh, okay, there we go. Fantastic. Okay, so what I'm going to do is... I'm going to make a table and just... If I need it, then it's there, right? I don't know if I will, but... Alright, so symbols... symbol BOL definition. All right. And then this is just going to be V. And then view unit vector. Okay. I recently learned mechanics of deleting a vtable with a known type and finals. The compiler's speculation types are insidious. Mechanics of deleting a vtable. Unknown types and finals. Right, I know what finals are. Sorry, known types. With deleting a vtable with a known type. Interesting. Compiler's speculation. Interesting. Yeah. Well, I'm glad you figured that out. I can imagine that would speed up your speed everything up for you at runtime, because you're not having to do this type of stuff. You're not having to do, dynamic casts and all that kind of stuff. Oh, crazy! Oh, get crazy pointer in direction. Instant light unit vector. Yes. So I've recently learned how to use things like what is it? Multiple for multi-important sampling. How to use multiple probability distribution functions to select ones that make sense after updating them. Updating some of them to be 0 for the particular for probability for low probability distribution functions to help with sampling, but it turns out that's all to do with offline ray tracing, really. You never know, though. It might be it might come in useful one day. But yes, we need the BRDF. Here we are. I'm excited. I'm excited finally to learn this properly, instead of like half learning it and never actually getting into it. Oh, it's gonna be good. It's gonna be good. Yeah, I put up with so much offline ray tracing knowledge to try and get to this. So here we are. Of a BRDF. So what I'm going to do as well, guys, is I'm probably going to implement this as I go in my game engine, because I don't see any reason why not to. So it's probably going to take a little bit of it's longer to complete than just reading it from top to bottom. What I'm going to do is just kind of speed through this by copying instead of typing it all out, because that's all I'm doing. I'll fix the all the text in a minute. It's copying some of the table with it. This is just so I never have to open this document again, so I can just refer to this. And we go down here, grab this, fantastic. All right, yeah, because I want to get into it really. All right, so let's clean up. Get rid of all this. Spherical domain. All right. Hopefully we learn about light geometry as well. That'd be good. And shadows and stuff like that. That'd be fantastic. I'm super excited. Whoops. Right, so we can't have that there. We have to do this in a domain. This. Because Obsidian thinks it's a link. Right, okay, so then I'm going to grab these two as... What is it, this one? No. Right, so... Really? Okay. LaTeX. Right, let's get rid of this as well. LaTeX dot product. Oh, music. Let me fix the... Put this back to about 40, which seems to be reasonable for people. And I'm going to throw this on. Alright, I've been enjoying this, so hopefully that's a chill with you guys. Alright. No, I don't think it's going to be on here. Dot product. Oh, it's just C dot, okay. And dot L. Okay, so slash alpha, and that is, we learned this one, did we? Sigma, and that's omega slash omega. And we have f of 0. Oh yeah, what am I doing? F of 90. And we have a x to the power of plus. Oops. Plus symbol. A. Oh, A, just A. And then N underscore IO there. And then alpha, right, in brackets. So that should be good. I know it's not the same, but yeah. Okay, so what do we have? We have roughness mapped from the import of perhaps roughness. We have diffuse, we have spherical domain, we have reflectance at a normal incidence, reflectance at a grazing angle. Okay. And heavy side function, which is if A is greater than 1, otherwise 0. The index of IR incidence of refraction. Oh, of an interface. I thought it was something else. Dot product clamp between 0 and 1. Saturated values clamp between 0 and 1. Okay, so here we go. This is what we actually came here for. Material system. The section below describes multiple material models. To simplify a description of various surface features, such as anisotropy. Anisotropy. Is that anisotropy? I actually need to look up how this word works. Just so I don't say it wrong over and over again. I think this is really loud. Can we turn it down a bit? Yeah, bear with me for a moment.
Anisotropy.
That's not how you say it. At all. So just have this woman read it out. Oh, come on, YouTube, please. Go. Anisotropy. Anisotropy. Really? It's anisotropy? Alright, anisotropy it is, I guess. Anisotropy, or a clear coat layer. Or the clear coat layer. In practice, however, of these however, some of these models are condensed into a single one. For instance, the standard model, the clear coat model, and the anisotropy model can be combined to a single form, more flexible and powerful model. Please refer to the material documentation to get a description of material models as implemented in filament. Okay, the standard model. The goal of our model is to represent the standard material appearance. Material is described mathematically by a BSDF, which is composed of two functions. Okay, didn't know that. Okay, so standard model. So some of the stuff I won't write down because I already know, but we'll see how much I know. So the BSDF is made up of two models. I should write these down, I guess, just in case I never refer to my other stuff again. Okay, so the bidirectional. Let's copy these out. Actually, it's gonna be fast because if I'm just gonna write out the text, it's gonna be faster. So, this does subsurface scattering. I wonder what the BSSDS does. Yeah. Fantastic. The BRDF. Okay. Since we aim to model common encounters, since we aim to model commonly encountered surfaces, our standard model will reflect on the BRDF and ignore BTDF, or approximate it greatly. Our standard model will therefore be able to correctly mimic reflective, isotropic, dialectics, or conductive surfaces with short mean free path. With a short mean free path, okay. The BRDF describes the surface response of a standard material as a function made up of two terms, a diffuse and specular. The relationship between the surface and the surface normal, indirect light, surface normal, instant light, and those terms is shown in figure 1. We ignore subsurface scattering for now. Okay, so BRDF. I kind of knew this, but I'll write it down anyway. Yeah, let's write that down as BRDF. Is made up of two components, FD and FR, F_R. The interaction of light with a surface with using the BRDF model with a diffusive and specular term. This okay. So this would look something like this with BRDF. Notes the note the surface normal N and the light L. Right, so I'm going to grab this, throw this in here, and just kind of rename it. Oh, it's got its own name. Nice. All right, cool. Next is the complete response can be expressed as such. This equation characterizes the surface response for instant light from a single direction. The full rendering equation would require to integrate L over an entire hemisphere. Okay. Yeah. Okay. I'm kind of on the fence about this. We would write the BRDF as FVL equals F underscore D VL plus FR VL. We, of course, would need to integrate over a hemisphere, sphere to solve this using under the rendering equation. Okay. Commonly encountered surfaces are usually not made of a flat surface, such as the model. So we need to model that characteristic and the interactions of light with irregular surfaces. A microfacet BRDF is a good physically plausible BRDF for that purpose. Such BRDF states that surfaces are not smooth at the micro level. Thank you, TT. But made of a small number of randomly aligned planar surface fragments called microfacets. Figure 2 shows the difference between a flat surface and an irregular surface. Okay, so a microfacet BRDF. Let's grab that. Grab all of it, actually. Oh, excuse me. Just get some water. So yeah, as we go through this, we'll improve our renderer, I think, or at least our implementation of the BRDF based on a light source. The only downside is I don't know. I'm going to just quickly look ahead for but when we're talking about lighting geometry, that's what I'm interested in at the moment. Yeah, because it would be nice to have this type of stuff as well. If I had polished metal, but because if they could do it on Android, I should be able to do it in on the GPU. Assuming that I have the same materials, same models to work with. Anyway, blah blah blah. So this is what I'm interested in. So yeah, point lights, which is good. Spotlights. Yeah, so this is what I need to know. I need spotlights. What else is there? Okay. Oh, I see. That's for I think lights and a light. Okay, lamppost. Okay, area lights. Okay, so there's no area lights here, which is kind of sad. Let's see, what else is there? Okay, so just a bunch of lighting, image-based lighting. So that's here as well. So that is the environment map. So this has got the stuff that I wanted to do originally. So it looks like we're just combining a bunch of models together here. Yeah, so we're just combining models. Comparison between top. Okay. Clear coat. Sorry, I'm being a bit scrolling through. So we just need to fill in the blanks basically of what this book doesn't give. I mean, this document. Because I have the sneaking suspicion that people are going to be like, "Wow, you're studying filament. Oh, that's so basic, bro." But it looks like a lot of most people have not implemented all these effects in their engine. Like all of them. Like maybe some of them, sure, but all of them. Yeah, I doubt it. Clustered forward rendering. Huh. Ah, okay. This was the. I think this is in the book I was reading. I kind of didn't get this far. So that's good to know. So it's got like multiple. How to do lights. How to deal with multiple lights. Yeah. Right. And okay, so these look like references. Okay, so yeah, I'm probably not going to read the. These are just I think these are just references, right? Yeah. What the heck? Yeah. Okay. So not that interesting. The rest. All right. Yeah, if we can pull off some of these lighting effects, then we would be a lot better off, I think. Right. Sounds good. Sorry about that. I just needed to make sure that we're not gonna have a repeat of the book we just went through, and it was just like it just went off on one. Why can't we scroll up? Yeah. Okay. So the area-based lighting we're gonna have to look up on a different place because that's quite important, I think. But at the very least, we need A spotlight, right? That is the thing we do not have, which is kind of help really not good at the moment. So yeah, it has pretty much all the geometry that we need initially. And then, yes, okay, so, right, blah, 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 blah. Okay. Let's give yourself a stretch. Alright. I always find it after I've eaten is like the worst. I'm most unproductive and like sluggish. Okay. It's a good physically plausible PDR. Okay, so this is a good PBR for our purposes. Such PBR states that the mic. Okay, yep. So it's not smooth. Excuse me. At the micro level. Yeah. They are made up of randomly aligned planar surface fragments called microfacets. Right. I don't really need a picture for that, but that's fine. Okay, so only the microfacets whose normal is oriented halfway between the light direction and the view. The light direction and the view direction will reflect light as shown. Okay, so only a microfacet whose normal is orientated halfway between the light direction and the view direction will reflect visible light. Halfway. Only microfacets whose normal is orientated halfway between the light direction and the view direction. Where's the light direction? Oh, really? So that means the only microfacets whose normal is oriented halfway between will reflect. Okay, will reflect. The rest will scatter. No. Uh-huh. However, not all microfacets with a property or However, not all microfacets with a properly oriented normal will contribute to the light, as BRDF takes into account masking and shadowing, illustrated here. Hi, Rashid. There. He said. Here, there, everywhere. Or did I write the wrong there or something? The light, direction, and I don't know. Well, anyway, with a properly oriented normal will contribute reflected light because of shadowing and masking. Okay, throw that there. Ugh. A microfacet bidirectional reflectance distribution function is heavily influenced by a roughness parameter, which describes how smooth, low roughness, or how rough, high roughness a surface is at the micro level. The smoother surface, or the smoother the surface, the more facets are aligned, and the more pronounced the reflected light is. The rougher the surface, the fewer facets are oriented towards the camera, and the incoming light is scattered away from the camera after reflection, giving a blurred aspect to the specular highlights. I see. I was busy in productive AI debates. Oh dear. I'm sure. Yes, it sounds extremely air quotes productive. With increased roughness, the specular highlights blur as the light reflected is scattered. As the reflected light is more scattered away from the camera. These pictures are fantastic as well. Yep. I was looking ahead at the filament stuff, and despite it being I don't know, if someone saw the stream and said, wow, bro, this is basic. I don't think many renderers that are in people's game engines do all what filament can do. By the looks of things, it's actually quite sophisticated. Yeah, it's got volumetric fog, which is nice. It's got light clustering. It's got a lot of different things, which is kind of cool. which you don't think. It doesn't have area-based lighting by the looks of things. It only has a couple of light sources and some fake ways of handling like lamps and stuff. But that's about the only biggest thing that's missing. I think if you had a renderer that did everything the filament did, it would be a really good renderer for most situations. Anyway. About roughness. The roughness parameter as a set of the roughness parameter as a set set by the user, sorry, is called the parameter that roughness in the shader snippet. Throughout this document, the variable called roughness is the perceptual roughness, with a mapping explaining in 4.8. People usually do area lights with linear transform cosines in real-time raster-based rendering. Yeah, I saw in Learn OpenGL that there was an article on it, I think. Yeah, so let's keep on. Oh, the stretch. Oh dear. Oh, the rendering equation is here once again. Though there is no good way to calculate shadows for them without ray tracing. Yeah, I might do what you do with ray tracing, but I don't know if I want to do the temporal stuff, so I'm kind of on the fence about what to do. But anyway, I got other things to worry about for now. Like plenty of other things that I don't know. Yeah, I don't have to worry about if I need ray tracing or not yet. At the very least, I don't need to know all the ray tracing offline stuff that I did. Anyway, microfacet model is described by the following equation, where X stands for the specular and diffuse component. Oh, I apologize. Oh my goodness, I'm not bored or anything. It's just after eating, I often get sleepy. The FTAA indoctrination is working overtime, I see. Uh-oh. In terms of D, in terms of, excuse me, I apologize. In the term of D models, the distribution of microfacets, this term is referred to as the NDF, or normal distribution function. This term plays the pivotal role in the appearance of the surface in figure 5. The G, I see. Okay, so these are this is each part of the rendering equation. Okay. Oh, he wants to play video games instead of do this, eh? You have the model you have two models, D and G. I should write out that equation. Okay, so this is just the rendering equation again, but with a different setup again. So BR and the cosine as a dot product instead. All right. F of x, v, l. All right, 1. And, oh. Now, are these normalized or absolute? They're probably normalized, but I'll never know. Mm-hmm. Okay, so we have int, and then we have omega. It sounds like to me as well with rendering that shadows outside of ray tracing them are one of the hardest things to get right in rendering. It feels like. Most temporal artifacts are causes of using old data when you should have discarded it. Oh, sorry, I didn't read the others. Temporal methods are just reusing work across time. You might not be able to sample 64. You might not be able to get 64 samples per pixel per frame. Mm-hmm. But you can reuse work over a bunch of frames to get the effects of more samples. Most temporal artifacts are using. I see. So it's just like skill issue rather than the technique's bad in general. If you can't pull it off without weird ghosting. And probably aggressive upscaling. That's gotta be a contributing factor. With like game companies being like, oh, we prefer to render to 7. You know, hypothetically the worst company ever. 720p, and we upscale it to 4K. You know, in that situation, because we can't get the rendering or the game to run fast enough. Aggressive upscaling does make it worse. Got you. I just I've never liked the blurriness that comes with going from 144p to 4K works fine. I see. But 720p to 4K looks terrible. Got you. Oh, excuse me. I apologize for being a bit. I'll perk up in a minute. It's like the afternoon lull. If you're familiar with it, where you've eaten, it's 2 o'clock, and you get sleepy for some reason, but at like 4 o'clock, 5 o'clock, you're completely fine again. Just is what it is. It's just a human circadian rhythm, I think. So, okay, so the term of D distributes the microfacets. This term is also referred to as the normal distribution function. Yeah, I'm willing to look into TAA and all that kind of stuff if I don't get smudgy imagey stuff and it's not insane to implement to get those effects, because if you get it wrong, it just looks bad, you know. Anti-aliasing techniques. The process of deciding whether to use old work or discarding it because there's too much change is called historical rejection. ML-based TAA algorithms excel at this specific step. I see. Like DLSS 2 and 4 and RDNA 4. Nice. Would you say my images look smudgy? No, it's more I would need to see them in motion. I'm sure they're fine, but if I was to spin the camera around, would the detail be lost? I don't like motion blur as well. I'm also a bit of a stickler for motion blur, so if you've got motion blur, I would usually turn that off in video games, and then and then I would start seeing smudging more often because there's motion blur when you move the camera is gone, so the smudginess of the effect is I think even bad TAA implementations typically look okay when still, but it's usually like I notice it the most personally when there's like foliage or something like that, like in a foresty area. And then I swivel the camera around in like a bunch of grass and trees and stuff like that, and it's like lots of small little, and hair usually kind of smudges as well. I'm a 0 to 10% motion blur person. Yeah, it depends on the game. I think for me as well with I like it more in racing games. When that's applied, it feels like it's actually going fast. But when I'm like walking around as a person, I feel like I don't like to think. It starts to get a bit nauseating when they treat the camera that like in third person games as a literal, like I'm a person carrying a literal camera. So there's got all those like motion blur effects to it, especially with low frame rate. So yeah, I don't mind it in racing games that much because they usually just do it to the ground, which is cool. Usually, but apart from that, no. I usually turn it off, especially if it's a 3D, a third-person game. This term plays a primordial role in the appearance of surfaces. I use 10% motion blur in something like Spider-Man PS4. Yeah, I can see that. Because the swinging through is kind of closer to a driving game. I can see that. Yeah, I can see that being kind of a nice effect. But personally, I've never played it, so I wouldn't know. But I would guess I would probably still prefer that as 0, just because of the when you swivel the camera around the player. I don't like the motion blur effect that everything gets when you do that in third-person games. Anyway, it's a little bit nauseating. Aggressive stuff anyway, so I just like to have it off. In terms of okay, so here's the occluded or shadow masked. Oops. Part of the micro facets. Not to tell a lie, even with the best TAAU will have some blur, but the visuals look more stable than other some other anti-aliasing with modern lighting. You see, it's a trade-off to make, like everything in real-time graphics. That makes sense. Okay, since I don't know what the trade-offs I'm going to make are yet, really. Should I have more janky shadows for clear images, or super crisp shadows with slight blur? No idea. Since this equation is valid for both specular and diffuse, the difference lies in the microfacets FM. It is important to note that the equation is used to integrate over the whole hemisphere at the micro level. I see. Okay, I just don't think I need to write that though. The diagram above shows that the micro level and the surface are considered flat. This helps simplify our wait, what? The diagram above shows that the micro level the macro level, sorry, I'm saying it wrong. The macro level, the surface is considered flat. This helps simplify the equation by assuming a shaded lit fragment from a single direction corresponds to a single point on the surface. At the micro level, however, the surface is not flat, and we cannot assume a single ray of light. We can't assume a single ray of light anymore. We can, however, assume that the incident rays are parallel. Since the microfacets will scatter light in different directions, given a bundle of parallel incident rays, we must integrate the surface. Integrate the surface response over a hemisphere. Note M is in the microfacet. M. Oh. Noted M in the above diagram. What did I just read? Oh man. Might as well get another drink. Wake me up a bit. I don't think it's not the documentation's fault. I literally just went blah, 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 blah. My brain, all the words fell out my ears, out my eyes, out my mouth, and all mixed up order. Anyway, since the microfacet will scatter light in different directions given a bundle of parallel arrays, sure, we must integrate the surface response over a hemisphere. Noted M is in the diagram above. Noted M is in the diagram above. Modeling the surface response at a single point requires a integration at the micro level. It is obviously not practical to compute a full integration over microfacets hemisphere for each shaded fragment. We will therefore rely on approximations of the integration for both specular and diffuse components. Sure. Okay, so it doesn't seem too dense with information, that. The micro level, however, the surface is not... Oh, the diagram above shows that a macro level surface is considered flat. This helps simplify our equations by assuming that the shaded fragment lit from a single direction corresponds to a single... Okay. To simplify things, we make sure that when a light ray hits a surface, we assume that the fragment where it lands is also flat. Meaning that a single light ray fires from that surface. Alright, cool. Right, I'm just going to grab a drink with a bit more caffeine in it so I don't end up dribbling on myself while I try to read all this. And then I'll turn this into a note, which is quite nice, because I am getting sleepy. But I think it's one of these things where I've just got to push through. And not give up. So yeah, I'll be right back. Won't be that bad. BRB. Blah 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 blah. Zoom in, zoom in. Alright. Oh, nearly touched the mic. With the speakers. Okay, back from the kitchen, which was literally walk around the table and go to the kitchen. Okay, right. So what I'm gonna do is I'm gonna come up with a new video soon to watch. Hopefully it's a good volume for you guys. Oh, you can't hear it. Okay, so how's that? You guys really can't hear this? Oh. Okay, hopefully that's better. Didn't realize how quiet it was. What are we doing? What are we doing? We are splitting up my notes into a something. Okay, so I think it's just like an introduction to what the BRDF is. Yeah, so I'm just going to grab all this and kind of make this into a introduction to BRDF. I wonder at what point in the future are we going to get full path traced real-time rendering? Because that's going to be a crazy day, because there's all these like techniques that we learn nowadays. So physically based rendering are going to be like completely obsolete by that point. What is BRDF? What is the BRDF? And then filaments. I wonder I have a feeling though that we would still get like PS1 era looking games. Introduction to the BRDF, and then we'll grab this fella, and we're going to put this in our graphics theory. Graphics theory. I'm kind of interested, just real quick, to if you don't mind me going on a slight tangent here, just look at this. Damn, that is looking big. It's making this look smaller. All the graphics theory. This is most of my knowledge when it comes to graphics programming now. Not all of it, but most of it. All here. Drop it in the middle. Nope. Make them touch. Anyway. Enough messing about. I just wanted to be a bit silly for 5 seconds. And let's get back into it. And restart the timer, which is yeah. So you can what is it? You know when you want to insult someone, you say like, "Oh, what you know about graphics theory is, or graphics is, we could write on the back of a post-it stamp." Well, there you go. What I know about graphics theory, you can write in Obsidian. I don't know what that means, but there we are. Okay. To better understand some of the equations and behaviors shown below, we must first clearly understand the difference between metallics, conductors, and non-metallics, dielectrics, surfaces. So dielectrics, dielectrics, I think. Looking at it, dielectrics, electrics, yeah, dielectrics, not die. Yeah, I was saying it slightly wrong. Are plastic, are non-metallic. Surfaces. And conductors. I mean, obviously I knew conductors, but oh, metallic. But I thought dielectrics were exclusive to like gemstone type stuff. I don't know why. We saw earlier that when incident light hits a surface governed by the BRDF, the light is reflected as two separate components: the diffuse reflectance and the specular reflectance. This modelization of this behavior is straightforward, as shown in Figure 7. Modeling Figure 7 modelization of BRDF as part of a BSDF. Modelization is a significant. Significant. A modelization is a simplification of how the light actually interacts with a surface. In reality, part of the incident light will penetrate the surface, scatter inside it, and exit the surface again as diffuse radiance. This phenomenon is illustrated here. Scattered light of diffuse light. The scattering of diffuse light. Here lies the difference between conductors and dielectrics. There is no subsurface scattering occurring with pure metallic materials. Huh. I had no idea. It comes to metallic, purely metallic materials. I might put on because this is about to end. I wish I could put on these Minecraft ones, but I guarantee I'm going to get copyright striked off the planet. Let's, if you bear with me, let's put on some. Yeah, I got an idea. Let's stick on this. I'll just loop this for now because I don't like the other two. Okay, it's a lot louder. Let's see. Yeah, it's too loud. Hopefully that's good. Let's see. Might turn this down here. Okay, so hopefully that's chill and not annoying. They do not do any subsurface scattering, which means there is no diffuse components. I wonder if a mirror is considered a a conductor in this case then. And we will see later that this has a influence over the perception of color or specular components. Okay. Scattering happens in dielectrics, which means they are both specular and diffuse components. Yep, makes sense. Oh, hello from France. I recommended you the composition of that guy. Right? Rohanai. I don't know if it's okay to play these songs on stream, but it's classical Iranian piano. It depends if it's copyrighted. The reason I play lots of video game music is because YouTube doesn't mind you playing a video game on stream. It wouldn't work if all the music was copyright striked when you played that video game. So that's why most video games are safe. If it's in the public domain, then it's probably fine. But even then, sometimes you can get copyright striked because or copyright claimed. I don't know what it's called. If the recording of a particular thing has been copy claimed or something. So some like film some orchestra what are they called? Some people who record stuff like say this is my specific version, so you can't play it. But I'll check it out. It does sound interesting. I need to check out this other one as well that someone sent me. But I'll write it down as well. I'll write this down. I was writing down some stuff here that's yeah, because I might at the very least check it out after stream. Because it's going to be and also greetings from the UK from someone in France. I hope it's not too hot. I've heard it's hot in Spain. Hope you're getting away with it. Because I've heard it's very, very hot today. Anyway, to properly mobilize the BRDF, we must therefore distinguish between dielectrics and conductors. Yep. Meaning we need to make sure we categorize, we treat these differently from each other. Scroll down. Oh, is that it? Okay. I don't think I need pictures, to be honest. I just need to be told what that is. Okay, so let's add another note to our growing list. What are... Okay, so energy conservation is probably pretty basic. Dielectrics and conductors. Okay, make this full size. Throw this in. Just a tiny little note. Introduction. Introduction. What is physically based around this filament graphics theory, and this is physically based rendering. Okay, so let's throw this in our theory section. Down here, pretty basic idea, but I like it. I like the way it's separate out. So we do not need this anymore. So energy, conservation. Okay, so this is, I think I already know what's going to happen here, but okay, so energy conservation is one of the key concepts of a good PBR, physically based BRDF, for physically based rendering. Energy conservation. The neck. An energy conservative BRDF states that the total amount of specular and diffuse reflectance energy is less than the total number of amount of incident energy. Incident energy. Without energy conservation, BRDF art. Oh my goodness. Without an energy conservative BRDF, artists must manually ensure that the light reflected off a surface is never more intense than the incident light. I kind of get this concept already, so I'm not really that worried. Okay, so whoops, a daisy. Specular BRDF, so I'm going to leave that. Yep, you've got to make sure your energy is conservative. You don't have more incident light coming out because it breaks the one of the laws of physics, but it's fine to have it within reason, I guess. Anyway, so I think to start learning how to do this, I also need to. I'm just going to run my engine just for a minute. Right. Whoa! I apologize for that noise. I don't know why it's making that noise. Let's turn that off for a minute. That scared the life out of me. That laser sound effect right to the dome. Right. So we're just not doing that sound effect for a minute. Okay, so right, cool. I also really need to. What I'm going to do actually is, okay, we're not deleting everything, which is annoying, but that's fine. For now, I know what this is. It's yeah, 24. Okay, so it's I know exactly what that is. It's the thing I've literally just added. So, but what I'm going to want to do is, I want, let's make a new shader real quick. So what I'm going to try and do is just add a fragment shader that kind of just does reflectance on one light source for now. Sorry, BRDF, physically based rendering on one light source. And I want it to be separate from the one I'm currently using. Otherwise, we'll end up in a situation where I just want to be able to like fully kind of just mess around with it without thinking. So core, let's see, core shader. Let's say new frag. Right, I'm gonna hit the Windows noise is gonna trigger. That's not you, it's me. Yeah, that was me. Just so you're aware. Okay, so that should be collected. So the idea here anyway is to obviously learn the theory, but I think at this point in time I'm not going to be too lost if I start implementing bits and bobs of things without completing everything. So yeah, we'll see. Or does it try and compile a shader with nothing in it? Yeah, that's fine. Or at least shows it's working anyway. What is going on here? Alright, so oops, version. So 460 and obviously void main. And what we're going to do here is we're going to have textures and roughness and all that kind of stuff, but we're just going to, for now, work backwards. So we're going to have pretty much everything in the old shader up until the point of which we... What is going on with my... I'm just going to close Visual Studio so I don't know what it's doing. Yeah, it's just all a bit weird then. I think you've been vibe coding Visual Studios for too long. So I'm going to take all this and effectively... It's kind of pointless me writing that, but... so what I don't want is anything that is not... So I need all the data still. So I need all the textures, emission, all that kind of stuff. And then anything after that point, I'm going to just delete. So instead of taking from this, we're just going to go, all right, cool. Thanks for all the fish, and delete all that, right? And what we're going to do then is, okay, so we're just going to take the base color and decode it back to low dynamic range, which I believe is what's happened there, and spit it out. That won't have changed anything, so all the data is still here. Yeah, okay, so we've done that. Now we need to go to... This is just like a more of a... this is going to make my life easier type situation. I just had to remember I've done this. But I guess I'll just have to put up with the fact that I might forget. Anyway, so just compile. No matching overload function for encode. I guess I don't have this then. I mustn't have brought over encode and decode and all this stuff. Let's see. What am I missing? So we have decode and get what? Oh, RGB, right? My bad. All right, let's see. So this should be, and I'm also going to go into game, and we're just going to have our fragment shader. Sorry, our non-player camera. So it's just easier to kind of do stuff with. We shouldn't have any lighting actually at the moment, so what I want to see is no lighting at all and nothing is black. Where is the... Okay, so we don't want to update the player. And we want a camera where we're doing this, and we want to update the position based on our free camera, not the player. That should now display everything as like colored in with no lighting at all. Yep. So that means when we start writing our functions, we can actually start to see. So there we go, right? Now everything's just got its regular texture with no lighting. And hopefully we can get something that's kind of like better than what we've currently got. So, yes, I forgot about that. while reading this fella. So let's dive back into it. So yeah, instead of just pure theory, we're gonna be also doing dev. So for real, we might just have a specular display for a while with no diffuse, which is completely fine for me. Anyway, enough ramble. Enough ramble. Right, okay, so specular. I'm probably going to take every time this, every time in this, what is it called? Documentation, it's going to say, oh, by the way, this is slow or whatever. I'm going to use the slow one because it's going to be more accurate because I'm not targeting mobile hardware. So, okay, so anyway, let's dive into it. So for the specular term, okay, so the specular term f of r in a mirror is a mirror BRDF that can be modeled with the Fresnel law, Fresnel's law, no Fresnel law, yeah. Noted F in the Cook-Torrance approximation of the microfacet model integration. Okay, so using the Cook-Torrance approximation of microfacet model integration. I'll do that in a minute. Integration. We can model. We can mirror BRDF with Fresnel's law. Fresnel law. Let's write this a bit better with Fresnel's law for RBRDF. That's not a D. Okay, so let's write this out. Okay, so F score R, this is the reflectance, V L is equal to frac D. So this is where we start to get serious. H slash alpha, which is the, in our case, is that allowed for you guys? No. I'm just a bit paranoid, I guess. So this is only for specular, so this isn't diffuse. You got to remember that. Because I think yesterday I was like, why is this not working very well? And I only had the specular component that changed, which was not correct at all. So the Fresnel thingamajiggy. Oh, I'm excited, bro. Finally. I get to understand this stuff I blasted through the first time. I'm going to go underscore 0. And 4 divided by, which is... Oops. Yep, that's 4. And C dot. Oops. V. Let's grab that. All right, L. Given the real-time constraints, we must approximate for the three terms D, G, and F. All right. We must approximate for the three terms D, G, I guess let's not be lazy, and F a fail. Let's have a look. Seems interesting. What? This has a completed. Krista has completed a great list of formulations for these three terms that can be used with the Cook Torrance specular BRDF. What is this? Oh, this thing? Okay. Or is it A? Sorry, I think it's A. Ah, okay. That's actually really nice. You can use for what? There's a great list of formulas you could formulations for these three terms. Okay. If I don't know how you do an external link. Can I just try and remember something real quick, because it's kind of tricky this. I barely ever do it. I'm trying to remember a note where I have done it. External note, external note, external note. According to this blog, I know. That's the first line in the note, and that's to do with, that'll be in, not graphics theory, that'll be performance, I think. No, it'll be in Vulkan, but it'll be under, yeah, these things. It'll be one of these. No. Oh. No, that's not going to work either. Oh no, it's pipeline barriers. It's part of synchronization, and it is. When I said one of these. Sorry, I'm making a bit not much sense right now. I'll explain what I'm talking about. Barrier pipelines. Yes, here we go. Oh no, not that one. Ah, there we go. According to this blog. So you do, okay. Single, okay, got it. Oh, wrong way around. Trust me, it's easier to look that up like that, like I just did, than actually try and figure out how to do a hyperlink on the internet. It's so awkward. Anyway, according to this article, you'll be able to see a list of formulas that are equations, I guess. That approximate different parts of the specular. BRDF. BRDF. Okay. There we go. With the cook torrents specular. I should do that. Cool. Normal distribution. Should I keep going or? I mean, I will keep going, but what I want to talk about here is the. I wonder where the diffuse part is. So there's the for now. Yeah, okay, here's the diffuse part, which I got confused with yesterday. So this is an improvement of the BRDF, which I probably will implement. Sorry, looking ahead again, I don't need to do this. I just need to keep reading. Interestingly enough, though, they kind of just... Although this is a full listing, what I don't get is the how to apply lighting part. Ah, you know what? You know why I don't get it? Because they don't talk about it until much, much later. They talk about it in... So I think I need to just rob. I'm just going to rob something real quick. The point lights code, just to make sure it's the same. And then we'll be able to process the BRDF. I just want to make sure it's exactly the same. So when they work out their BRDF, we have a light to reflect that. I will go over the geometry stuff properly and do it correctly, but so they have point lights. Okay. Spotlights. Okay, there's some shader code here. So get. It might be worth learning this first, maybe. The reason I say that is because yeah, I'm gonna take a pivot and learn some of the lighting code first, and then I'll be able to kind of add in the BRDF on lighting geometry once I've worked it out. In fact, okay, This is literally the simplest. Sorry, this is super basic lighting. Okay, yeah, we could just do an ambient light. Yeah. I'm interested in the geometry. Where's the... Okay, so the fragment position... Okay, so there's a normal, there's a light position. Yeah, because you need to know the lighting direction to do any type of lighting at all. So what might be worth doing is... So I'm kind of on the fence here. Give me a minute. What's the best way to do this? Yeah, because I could do all the BRDF, but I need to apply lighting to it, and yeah, I know that at the very least. Okay, there we go. There's some kind of lighting there. Yeah, so there we go. There's the BRDF kind of illumination, intensity, normal direction. Let me think about this for a bit longer. Okay, so dynamic directional lights are particularly cheap. Get to evaluate at runtime. Sounds good. So what I'm going to do is just hard code this in and just have like a directional light in the shader. Because I need to apply lighting. So we're just going to rob this for now. And we're just going to take, I assume this is a vector, so I don't really mind the direction. I don't think it makes sense to do it based on my movement, so yeah, so I want the light intensity to be let's see, so they have, what do they have values wise? They have so without reading this, I don't quite know. So if I take in the base color, multiply it by this for now. Whoops. RGB, right? Multiply by illumination, which is light intensity. So I'm going to put this at what? Float 10,000. Let's put it at 10 actually. Let's make it really dark. See what happens. And no, light intensity. The L dot. This is just our L vector and N, which is our normal vector. Clamp to a particular direction, and our light direction is going to be. So this is going to be now this, and so light direction is going to be something like. Let's just do a random vector. I don't really know. Light direction is equal to 1.f, 2.f, 3.f. I have literally no idea what this is going to look like, but let's do a yeah, but it is a little weirdly. Okay, so there we go. Now I don't know what this is going to look like because we have no lighting. We're just doing something with the base color, but let's see. Okay, so that's good. Right now this completely destroys the image, but at least if I turn off the debug geometry, we have the materials lit. Now, why is it all lit in different directions? Well, because that's I think I need to turn down the intensity. It's way too high. That's because I've randomly rotated everything. So that's really good. That's actually what I want to do, because then I can apply the BRDF. So let's do this to 4, and I can actually test it then without having to worry about lighting geometry. So we turn this off. Yeah, so it should be lit. Yeah, that's good. Okay, so obviously we have materials here and we're not dealing with them. This is probably the cheapest light you can possibly do. But yeah, this is inaccurate, to say the least. It does look kind of strange though. I don't mind. I don't hate it. If I had to squeeze the most performance out and still needed lighting, this is what I would do. Just fake it with some random direction vector. Alright. Yeah, okay, so to get this to work, I would need to pass in the direction through the shader, which I'm not going to do. Perfect. Okay, so now when we start building up the BRDF, we can actually see the lighting. Very nice, very nice. Because we have the lighting director, we have the direction, we have the normal, we have everything that we need to start implementing it nicely. Okay, perfect. I'm happy with that. I'm glad that worked. That was a massive hack and a half, that. So our hacky lighting is lighting direction is in. So when we start adding specular BRDF. Right. Yeah, let's break this up into little tiny bits because it's easier to read. What is specular BRDF? Right. Yeah, because I would rather have like smaller notes, to be honest, than bigger notes, so I'm actually fine with making everything small. Oops. Physically based rendering. So let's go to our graphics theory and kind of grab these three, because these kind of need to be together. Oops. Yeah, I know it seems silly, but like I made up that I was able to just pull that off like real quick. Why? Despite it being the crappiest lighting. It's more that I was just able to kind of know what to do based on studying. So it feels like stuff is starting to pay off even just a little. That I was able to know that we need geometry. We need to figure out the geometry in the direction of the light. Why is that being... Oh yeah, what is specular? Which... I might split this up into like specular and diffuse and Fresnel. Or shall I just do specular and then just do all those together? I think that's a good way of doing it. Yeah, because by the time we can end today, maybe we can get that far. Or at least get to not necessarily the diffuse component, but geometric shadowing. Sorry, I'm just trying to figure out what I should do. I think I'm just going to go through it normally and slowly build up. Even if I just end up with one function written today, we should at least get the normal distribution function D working, right? Which I don't know how that's going to affect lighting, but if it's just by itself, definitely not physically accurate, but yeah. Anyway, enough talk, more study. I'll tell you what, this is lovely compared to the book I was reading earlier today. Well, yesterday. Instantly usable knowledge and not that complicated, really. How are you liking Filament so far? I'm liking it a lot, actually. It's just so much easier to understand what's going on than that other book I was reading, which is like a torture book in comparison. So far so good. We've got like I was able to, I don't know if you were here actually, but I was able to just kind of know what to do based on my basic lighting, and I decided to just throw in some random direction lighting. I was like, based on just what I read, I was like, oh, now I can start testing if the if the PBR sorry, if the what is it called, BRDF is going to work based on the geometry of the lighting that I just did, because I just did direct, like, random direction lighting. Like just a good, like, and I was just like, okay, this is just making everything make sense across the board, like, oh, I see only the, oh, I see one of the half float memes to there. That looks better already. Ah, thank you. Yeah, it's starting to get there. I haven't even implemented good BRDF yet, so yeah, I'll have to watch out for the half float thing. I'm not exactly sure where it is, but yeah, I'll keep my ears pricked up for it. All right, so let's keep reading. Burley's observed a long tail normal distribution of the NDF. The normal distribution function are good to fit the real world surfaces. GDX distributes describes in Walter 07. The harsh light does kind of fit for space. Yo, thanks guys. I didn't expect the just the random direction lighting I threw in to look decent. The only thing I don't like about it, which I can easily fix because it's not a, you should see the shader. It's pretty silly. The way I work out the directional lighting is just a random vector, right? So if I was to give the pass this in rather than have it just like here, then we would be able to see. But the only like I said, the only downside is it's like it's like everything's facing the, like, light is facing the wrong way in different things. So the shadows, the surface is lit up kind of weird, but I think that direction's quite easy to fix. But anyway, I'll keep cracking on. Yeah, you don't have that much ambient light in space. Yeah, that's a good point. Yeah. But there we are. Anyway, it does look better than just black. Anyway. Excuse me. So yeah, let's keep on keeping on. Okay, so okay, so the DDX distribution described in Walters. So in the ND normal distribution function. Hello, Mado. How you doing, dude? No, I'm not. No, it was literally just a hack. Just to get some geometry in the scene, some light geometry. So we will be transforming the direction based on, you know, so things don't get weird. Yeah, it's literally just a hack at the moment. But I'm I'm still kind of glad that you know initially saw it was there, thought it was good, even if you don't think it is anymore. So yeah, using the world coordinates direction for model chords in the yes. So it's all scoffed deliberately though. It's what was this quickest thing that I could get in to get some light geometry, and so I actually test things for everything really. So long tail, normal. Oops. Yeah, I will pass it in through the shaders and get it kind of normal looking sooner rather than later. Oops, what am I doing? Long-tailed. Is a better fit for real world surfaces. The DDX. I keep wanting to think of DDX, you know, Dance Dance Revolution thing. You don't transform a directional light. Yeah, but I would need it to be consistent across all the models that I've spun around. Right now they're inconsistent because I'm randomly spinning around the objects, right? So the vector at which the direction is facing is different for everything because it's rotated. To be honest, I wonder why you seemed like the light wasn't coming from the same direction. Yeah, yeah, that's by design. Just for, I'm not going to transform the light. I'm just going to make sure the direction is facing the same way for every model, rather than because everything's rotated already. I wonder. Hang on. When's the rotation actually? Okay, no, this is not necessary right now. All I need to do is make sure that when I do a BRDF function here, that we have some light that's lighter and darker in different places. That's all I need. That's all I need. Yeah, I'm already wanting to make it better. Failing miserably. I'm fine, thank you. Failing to understand textures and descriptor sets, though. Yeah, it's tough. It's textures are harder than they're much harder in Vulkan than OpenGL. They're not impossible. Anyone can learn them, but it just takes a bit more time. Okay, so with described in but yeah, good luck with that, man. It's I was thinking about this, right? As you get better, and not only this is maybe a bit too spiritually. As you start to succeed in life, which includes becoming a better programmer, like you'll face harder and harder. The universe in general will give you harder things to face because you get more capable. Bit of a weird way of thinking about it, but I kind of like the way that in programming, like, it's kind of the same thing. Well, it is the same thing because it's part of it. It's in the same category. Because Mabdo, you've leveled up. You're like in you're not in the beginner zone anymore. You're in zone 2, where the enemies are tougher. The final boss is harder. Now you have to deal with textures, which beginners don't have to deal with anymore. You're off tutorial island when it comes to rendering a model. So I wouldn't be hard on yourself. You're now facing harder enemies, if as to put it in game terms, and stuff like that. So just be aware that the harder issues come due to progression, and only through struggle can you grow. So it's good that you're. So the fact that you're failing miserably is unfortunate, but also kind of necessary as part of the journey. So yeah, good luck with that, dude. You'll eventually become the graphics programmer you're meant to be if you keep going. Which you never know. You might come up with new lighting theory or implement something really cool that everyone likes, or whatever. So to do that, you need to be able to go through each zone as it gets progressively harder. Just like a video game. Zone 2, Zone 3, Zone 4, Zone 5, etc. The final boss never gets easier. It always gets harder. But you're perfectly capable to overcome it. Yeah, but you're capable, dude. You're 100% capable of learning it. There's no... I have no doubt in you at all. The fact that you're facing it is proof that you're already capable of it. You just have to overcome the friction. No, the finer, the hotter the fire, the finer the metal. And each time you level up when it comes to your rendering, you'll have to face harder and harder challenges. I just want to design my game, and here I am waxing philosophy. Anyway, that goes for anyone who's listening, by the way, and it goes to me too. Anyway, with a simple formation suitable. I've just been thinking about that recently. Okay, so the GGX distribution with a long tail off, fall off, and peaks highlighted with the GGX distribution with long fall off and short peaks in highlights with a simple transformation for suitable real-time implementations. The popular So I think there's a better one than this, but I'm going to go with this one for now. Popular model is the Trowbridge. Distribution in, I don't know how modern this is, but I think it's pretty old. I'm just gonna say I'm not gonna add that in because it's going to assume that this is actually, so this is this, so D underscore GGX and then H alpha. And this is what alpha squared. Yeah, I'm well excited to get this looking good. Sorry, I keep saying that, but the reason I keep saying that is because, oh my goodness, the book that I was reading before has just made me like so it's such a struggle. I'm just so glad that I'm able to like, oh right, yeah, I can just do a thing now. Holy, if I just read this one instead. I may not be the best graphics programmer, certainly not. You could say I'm rubbish, but now I'll be able to at least write my own version of this thing with and understand it properly. Alright, +1. Alright, so let's write this out in code. Now, unfortunately, there's no extension for GLSL. Why is this D? Simple and efficient. Oh, it's the, I see, it's the D function GDX, I see. GDX. Yeah, I don't mind this. Yeah, I don't think GPU class, desktop GPUs likely use this, but it is nice to at least see where we come from. N, oops, NOH. Roughness. I don't know why it keeps doing that. It's like a new feature that's kind of broken. So K. And so this is the A, and this is the K. Right, okay, so this is just the... How is this translated? Why is it K hitting it? Whatever. I'll write this out and I kind of reword it with variables. And 0. N O H. So to do this, we need a half vector, which means we're going to have to pass in more than just... Alright, so I already know kind of what to do here. So I'm just going to take... I don't know how how this is going to affect the lighting, but... K times K at 1 over pi. Alright, so we need... Okay, so we need... I think what I'm going to do is maybe... Right, so I think we have pi kind of floating around here. Let's see. If not... Yes. Okay, so we have pi. So let's write our first basic GDX, I guess. But to pull this off, we need to be able to get the directions of everything. So yeah, that is the next step, I think. So the half vector is the light vector plus the, which in our case is, so our light direction is L, and I don't know if it's normalized, I don't know. Alright, so let's write these out, right? L dot N. Yes, okay, so L dot N. Okay, so we at least have L dot N here. So I'm going to take these kind of and just kind of throw these together. So we do. We want H, and I'm going to move this like this, and yeah, we'll do it like this, I think. Whoops. And yeah, so we'll have L, 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 and then, oh no, wrong. I need to be changing everything. N, my bad. So we got H, H, V, viewing direction. That'll be I think. Where's our viewing direction? So we have the tangent, bitangent. If I look at my old shader, I should be able to find it because we have the same idea really. Yeah, what's V? What's that vector at? Okay, so it's just capital V. Okay, yeah, it's just A. That is our viewing direction. And that's fine, I guess. So V. And V here. Alright, cool. And that means we can... obviously, that's still going to do the same thing as before. Let's just check. We just need all the directions. Yeah, okay, so yeah, that has done. Everything's normal. Okay, keep forgetting that. Okay. We have the GDX function. We're going to write the basic GDX function to kind of build up. I know it's not what you typically write, but so I've already written this, but it'll get me some kind of, like, no one uses this, I believe, in GPU GPU class things at the moment. So, and just so I understand how you absolutely implement this, what's the base color? That's the question I don't know. How does this interact with base color? So assuming that we have specular stuff done, where's the base color come in? So let me look at my lighting code again. If my base color light intensity is in lumens, I proportion it. Okay. So let's look at my code for a minute, because that's going to probably make things a bit clearer. So when we are doing all this, assuming that we've got the BRDF here, there's the diffuse, there's the specular. We multiply. Oh, I see. So the diffuse is this, and then we multiply the specular and the diffuse. Okay, so in that case, I'm going to make it so the diffuse is just the default color for now, and that's going to be fine until we have a better solution. We're going to keep building up the solution until it gets better. So, okay. So this is our... Obviously, we wouldn't do this like this. We need the roughness, not the squared roughness, but actually the roughness, which is the guy we need as the second argument, and the first argument is the NH, so the half vector. So this should be part of the BRDF, but not the complete. Oops, not that, that's comma. Okay, so I'm kind of curious now, like what this does. We'll see. It's probably gonna do something weird. Whoa, didn't need to spin around. Oh, interesting. It's definitely decreased the harshness. Okay, so let's do this in steps because this is going to be interesting. So this will be base, because I kind of want to see the difference. It's going to be interesting to know. So with GDX at the basic of the most basic level, let's just see the difference. And I go to this. Yeah, it looks incredibly, I think. Yeah, because there's no specular at all. It's really harsh. And if I kind of add GDX at the very least, then we have, yeah, everything's a bit darker by the looks of things. And some of the things seem lighter, interestingly enough. Yeah, some of it seems darker, so I don't know. Yeah, it's just interesting to see, basically. Yeah, it's much darker, the scene. Okay. Enough having fun. Hey, do you reply to Discord DMs? Yes. I do. Not always immediately, but yes, I often I do reply to DMs, yes. But not obviously on stream. Because that would be distracting. Okay, so that was a bit of fun. So let's what else do we need to do? So I did Lambert's diffuse 1 over pi in my other game, in my other shader. Right, okay, so next is whatever was next, okay. Okay. We can improve the implementation by using half precision floats. I see, so this is the meme. This optimization requires changes to the original equation, as there are two problems when computing the one. Why has he not done the whatever in halves? First, this computation suffers from floating point cancellation when is close to 1. Secondly, n dot h does not have a precision around 1. Okay, so the solution involves Lagrange's identity. So x product is equal to, okay, a bit of vector math there. Since both n and h are unit vectors, yes, yes, because I assume that, yeah, okay, so that's the length. squared. This allows us to compute n.h directly with half precision floats used by symbol cross product. Shows the final optimization implementation. We don't need to do this at all, so I'm just going to leave that alone. Not going to even write notes on it. Implementation of specular D in terms of GLSL optimized for 16 flutes. So yes, if we needed to 16 floats, but we don't need to do that. Okay. Do I need to add? Yeah, let's add another note. Yeah, but yeah, there is a Discord server, by the way, for people who want to get in contact with me. You don't have to reach out over DMs. If you post in the org Discord server, you're more likely to get, when it comes to graphics programming especially, a better sample size of like more skilled people. Just because I can't know everything. Not that I even know anything useful at all, really, for what you're doing. I don't know. So there is that. So just to add that to the do you reach out to DMs. Sometimes it might be better, even if you're feeling shy, to post in a Discord server about your programming problems, because otherwise, you know, I can't solve everyone's problems when it comes to programming stuff. Oops, that's we've missed one, I think. But yeah, I do reach out to, just to finish what I was saying, I do try to be cordial to people who want to talk to me there. And as long as you respect my time, that's all good. I might say no if you want me to solve your university problem or something. If you know what I mean. Like, can you do my homework for me, kind of thing. No, I'm not doing that, but I'm totally chill, like talking about stuff and helping you out where I can. Okay, so let's keep going. Okay, so geometric. Oops. Oops. Shadowing. G. Eric Hertz showed in Hertz 14 the Smith's geometric shadowing function is correct and exact. G in is correct and exact terms in G. Okay, so the Smith formulation is the following. So oops, geometric, not radical spelling things like that. So Smith's geometric shadowing is correct, oops, and exact. In terms of G. It looks like G_1 L alpha and G underscore 1 V underscore alpha. Okay, let's change the music a bit. I feel like I've been listening to this for an hour. So let's go with blah, blah. I'm gonna risk it on this one. Hopefully it's just not this filing shrine over and over again or something. Oh, okay. I thought it was something else. Okay. Fair enough. 1 hour left. Let's keep going. Okay. So we have a G1. Let's go 1. Can turn the following into several models, and is commonly set to the GDX. What? G1 in turn follow several models, and is commonly set to the GDX formulation. The full Smith GDX formulation thus becomes... Okay, so is more than one model and is commonly set to the GDX equation. Okay, let's throw this in. G underscore 1 V A, that's alpha, sorry, is equal to G underscore and then alpha again, backslash equals frac do that 2 N C dot V. Let's grab these again. Actually, I don't need the brackets, but plus the square root. Right, hopefully this works. Square. Fantastic. So alpha squared plus 1 minus... I don't know how useful this is to have, but here we are. It hopefully explains this, because this might just set us back to where we were. Just kind of half understanding this thing, and then kind of it breaks, and I don't know how to fix it very well. So that is also that squared. Fantastic. Okay. I should be able to just grab it out instead of typing it out. Let's just check. Yeah, there it is. So let's do that again. So if I grab that, so I'm just going to test this out. No, okay, so it's not quite right. No, okay, so that's only useful in a limited situation. Okay, I was just checking that to help with speed, but no, if I'm gonna have to go back and fix it anyway, it's just gonna take just as long. Type it out. Okay, this full Smith GDX equation is, so when we're doing this, are we I'm confused a little bit, to be honest. Let me just check ahead just to see some code. So, so V. Okay, so yes. Okay, so this is a slightly. I know VXD. This and this multiplied together in this case. Okay. Okay, let's okay, let's type this out. Sorry, I was looking at something on my other computer, for just making sure everything was good for the stream. Looks like we're all good, guys. Okay, V, comma alpha equals G underscore GDX. So what we're doing here is just making sure that my formulas make sense. Oh no, what am I doing? This is the same. I'm writing the same thing out twice. So alpha A L comma. Man, if I had more time, I'd play a lot more Dark Souls. Sorry, Souls games. But here I am. My chosen path in life is to get as good as I can at this. So I have to commit. Or what would be the point? But at the same time, there is this committing purely to the craft could end up being detrimental to your games in the long run. Okay, so this is literally the same, but with a different component. Oh, hang on. No, it's the same. It literally is the same. It's n.l plus. All right. Okay, so let's just what I can do then is grab this twice and just modify the variables, I think. And then do a plus. Oh no, it's multiply, okay. So multiply these together. Nope. Let's get rid of this GDX thing. I'm gonna do this just to be absolutely. It's a bit rudimentary, but hopefully it's oops. Like a bit childish almost. Let me throw this into Notepad. I think I've copied too much here. What am I missing? Oh, okay. So it's we doubled up here. It's confusing the LaTeX. So hopefully, yes. Okay, fantastic. Now instead of that, we do L. Oh, get rid of this extra equation equals thing here. And we have, instead of NL, it's NL now. I believe it's the same. Alright, I'm just going to close this. It's going to make a Windows noise. It's not your computer. Oh, no, it's not. Okay. No Windows noise required. That was your computer if it did make a noise. Or at least I hope it was. Someone else's computer made a Windows noise near you. Anyway. What am I talking about? Okay, so we have, just making sure all the maths is the same in every single case. Yes. Okay. We can observe that the dividends of 2.nl and 2.nv can allow us to simplify the original formula of f underscore r and introduce a visibility function. So did we have that originally? Let me just check in the rendering equation. No, we didn't. Okay, so what is this v function then? As respect to things, what's going on? Because I want to understand this properly. I think my laptop is charged enough. Don't want to kill the battery. So we can observe that the dividends, dividends even. Is that right? Anyway, the denominators, I guess, allow us to simplify the original formula of FR by introducing a visibility function. Okay, so V. Okay, so this is the. I assume. Okay, this is the V version. Okay, so where the visibility function is G over the for these things. Normal dot vision dot times by normal dot light. V1 is equal to roughness times by. Okay, what's V1 then? And V1 is equal to. Morning, Mika. Hope you had a good night's sleep, dude. Good to hear. Good to hear from you. How are you doing, dude, Mika? Are you having a good day so far? Okay, let me think. Okay, sorry, I was just a bit distracted. I need to. Okay, so we can simplify things down because of and let's get the other one. Day just started. Well, I hope you have I hope your day chilling in bed. Hell yeah, brother. Love to hear it, man. Thank you for joining us, by the way. Well, hopefully I can entertain you while you're chilling. What we're trying to figure out here is how this visibility function, when we're working out the reflectance of our reflectance part of our BDRF, how that is simplified. I don't quite understand. So we can observe that these two allow us to simplify the original equation by introducing a visibility function. How do you know this? Ah, hang on. NV, yep. I see. Hang on. So if we have alpha... Okay, so these are the same functions twice. I see how it's working now. So how this is working is we're multiplying these two together, but these becoming the denominator somehow. That's what I don't quite understand. Effectively, we've taken this formula and we've taken out the denominator, the numerator, and somehow multiplied them together at the bottom. Now, if I do my algebra properly, I think this is literally an algebra simplification, right? That if we were to divide okay, we can create another fraction, or another fractional function, and divide it by the original. Oops, I get rid of this one as well. This is not correct. G. G function. Then through algebraic, through cancellation, we can simplify our GDX. Function. Okay, so why is this? There we go. Yeah, it's spaced too much. Okay, so what I'm going to try and do here is kind of extrapolate this out a bit. So instead of writing it like they have, I'm going to spend a little bit extra time just to go through the algebra. I hope that's chill, because otherwise I don't want to be the guy who just blasts through things and just doesn't quite understand them. I want to see it simplified myself. There's no light in space escape point in the story. I see. That's how we do it, yeah. You just bump into stuff to find where things are. Alright, so V, comma L, comma alpha. Oh my goodness. So we have 4. So N C dot. Oops. V. Very good. And so I'm going to extrapolate this out, right? So instead of having There we go, like this, right? Instead of just saying that's equal to that, which I will do actually for now. V underscore 1. This I'm gonna like write them all out. So this may be LaTeX. This may turn to LaTeX hell in a minute, but I think it's gonna be beneficial for me in the future. Multiplied by V. Okay, so that's like it's simplification down. Where I think I will go this far. Yes, so we can take one of these fellas and throw another LaTeX down. And there we go. V1, sorry, V comma alpha equals that. Okay, so now we're going to start. Well, lights need mediums to travel, correct? If it is the void, how do they travel? Yeah, well, it is the void engine. That's true. My engine's the void engine, so. Oops, I've left the fractional. I see. I think I just understood something further. Where the denominator denominator is, that's not how you spell it. Who would have guessed my first language is English? You would have assumed it was Klingon by the way I spell words. The visibility of the specular lighting for GDX. Smith GDX. Yeah, denominator, 100% no, Mado even. Right, okay, so let's do the algebra, right? So if we take G, so this is where things get mad. We take that, and believe it or not, I'm going to say equals, so we just get rid of this for now. And then, which is, hang on, that's the top, so we need to do another fraction. And that is 4. So let's at least go 1. So we need another fraction here. And like this, and we should see that. So you have 4. I'm doing this on purpose so I can C dot V. So hopefully my algebra kind of plays ball today. And then L. And then 1. Okay. So then if you want to do that. So this is a multiplication. So the next step is to simplify this down. So one step closer. Whoops. Copy. would be to not put these in fractions anymore. And what I'm trying to do is cancel the top terms based on this fraction. So then that would be so we flip the reciprocal over on this side, cut, right, and okay, so we removed our fraction, so I believe we need everything up to the, where is it? This? Yes. But because this is more, we want to put a bracket around this. And this, I think. And then times, I guess, if I'm going to stick to that. You should be able to see that the top and bottom terms of the outer fraction, fractions cancel out. Right, okay, nice. I think I'll leave the rest. Because if you multiply both, because if you multiply both sides by this, then I think and then you just distribute it, you end up getting. Is that right? Oh yeah, you would have to maybe multiply this together. But I think everything cancels out anyway. I don't know what order you do it in, but yeah, anyway, so. Anyway, okay, so hertz. Notes, however, that taking the height of the micro facets into account correlates masking and shadowing. Shadowing leads to more accurate results. Okay. He defines the height correlation. He defines the height correlated Smith thusly. Okay. From which we can derive the visibility, the visibility function. So by replacing cosine m with n dot n, I'm really tempted just to be like, yeah, bro, sounds great. I'm gonna just just because I'm curious, I'm gonna blast ahead just a bit. You shouldn't do this, but I am kind of curious. Based on what I've I just want to see what the end result will be based on this particular implementation of BRDF. So I'm going to throw in, we don't need this, and I'm just going to throw in this. Don't do this, guys. Actually learn how to do this. Yeah, but I am curious, like, ooh, what would the colors be? So L, O, H, F0. Oh, yeah, the F0. Which would be what? Wheat. So Lambert's. So wait, okay, so this is for F slick. I think we had this problem last time, didn't we? But F0 represents a specular reflectance normal. Reflectance at normal incidence and the achromatic dielectrics and the chromatic for metals. The actual value depends on the index of refraction of the interface. The GLSL implementation requires a use of POW listing here. Let's see. Where's the listing? Oh, listing 5. Okay. So in my older shader, what did I do? I'm just kind of curious. For the... Ah, okay, so I use that. That's why we have 0.5. Interesting. Let's have a look at the function again that I'm supposed to be writing. It's... Okay, so we have the U value, which was what? LOH. Okay, so and then F was I think it's a vector though, isn't it? Oh, it's not. It's so I say for the generic case the 0.4 for most dielectrics. Okay. Or 0.04, I think. Where's the second argument? What are you talking about? Oh, no, it is a vector. I think in my code I do something different, right? I take... Let's compare. Hang on. Okay, so I don't quite know. But if I look at... Whoops, sorry. The code again. Okay, so... Okay, we have that. And his false shader implementation doesn't define what F0 is. That must come from, in that case, the shader itself. And if I define a dialectic value of, let's just find like the most common dialectic vector, right? So like common liquids, I's default value. Like instance of reflection, so that would be for metals. So I think we need to pass in more data maybe. For conductors in the future. Otherwise we're going to end up with everything kind of looking the same. And we're not going to get any like metal look for anything, right? So other dialectics, right? It's just so yeah, if I went to 0.4, which would be just assuming that every single all right, so let's just mess with it because I'm kind of interested to see. Sorry, I'm rambling a bit, but what I'm trying to say is if we have a f of 0, which is I think the dialectic value that we end up doing, if we just derive it from the instance of reflectance value and get a value of and we do f I'm just going to duplicate this once. So FR is the official times by luminance. And I think, yes, we have FDR. Okay, so what would be... Yeah, we've got the IR value, but I don't think... The IOR even, sorry. We don't have a... let me think. So that's how you work it out. But I don't think I have this when I pass it in, which is kind of tricky. The instance of reflection. I don't think I have an instance of reflection that I can do with working this out, to be honest. Let me just work this out a bit more. So yeah, they do reflect in 0. Okay, so let's see if we can spit this out. Obviously we don't have reflectance. I think what that is going to be is just generic for us. What I mean by that is we're just going to figure out like a basic reflectance value, and then we can slowly improve this over time. So a reflectance value would be something like really low. It looks like 0.5%. What's that map to? Sorry, I'm being a bit... I'm just trying to get something to display, which would be nice before it's 5 o'clock. That's the goal anyway. That's why I'm going a bit faster. I'm being a bit clumsy. Did a lot more coding than I expected today, to be honest. Okay, so 1 minus metallic. Okay, yes, that's the remapping of the color. And I don't think we have the reflectance, to be honest. We have metallic, which is the metallic texture, which is in here somewhere. Where is it? Normal. Yeah, I legit don't think we have it. Yeah, metalness. That's what I call it. So, base color, RGB, and then metalness again. But the reflectance factor is not something I have, which I think is just... I'm just gonna have to guess, bro. I think it's a low value. Let's just go with something simple, right? If it's really bad, we'll be able to see, right? So 0.5, right? Half of 1, right? That's a decent guess, I think. But this could be completely like not right at all. And then you want V is redefined, okay. So V test. Just gonna deal with that. And we should have specular. And then we multiply these two together. So we have the Lambert diffuse and the full specular BRDF. And we do that based on the luminance multiplied by the direction, which is just some hard-coded value. Let's see what that looks like. The reflectance might be way too low or too high. Wow. Interesting. Let's go with... What did we do last time? I think we just did a rubbish... Okay, so for Flanell okay, term relies on f of 0, the specular reflectance at normal incidence angle. The achromatic dialectics, we will remap the dialectics described in this. What's the reflectance there? I don't know. Oh, if I turn this up to like 100, like 10, is this going to be no diffuse at all? I think that might be the case. Oh no, okay. That worked. That is pretty intense though. Yeah, it seems accurate. Well, accurate-ish, you know what I mean? It's like, obviously not perfect. These are very non-shiny objects, right? I would need to have a shiny object to see how nothing I have really is shiny. But anyway, yeah, it's, we're getting there. I just wanted to see how different it is, but I need to know more about the reflectance, to be honest, to be able to do that properly. Because the reflectance factor might be, like, I don't know if 10 is good or what, if that's too reflectant, what, or how that affects the specular. But anyway, I will leave that alone for a minute and just kind of go back to what we were on, which was just our basic diffuse. This is what we were on before, which is almost the same, but it's just a bit flat. We don't have any... yeah, I think the reflectance was 10, like way too high. And eventually we're going to have like different objects. So anyway, and also the angle's really harsh, and also it's not accounting for the rotation of objects. That's why everything's off to the side, you know, lit up differently. But that's by design. That can be easily fixed. We just have a big directional light at the moment, which is actually, honestly, for the game I'm trying to make, is actually kind of better than what I had before with one just giant point light. So I might stick with that for a while. But we'll see. So yeah, there are some issues with that, but anyway, let's get better as a graphics programmer, rather than just messing around with values. Yeah, because that's what I need to check. Like, we have like objects down here, like super matte, apart from the slight speckles of what is it called? Reflectant stuff in the asteroids, which looks really cool. But what I really need to see is metal, something metallic. Anyway, right. Okay. So what I want to figure out, what I want to learn is this. This is kind of tricky. So what is Hertz saying here? Hertz, however, is taking the height of the microfacets into account. Ah. Okay. To correlate masking and shadowing. To correlate with masking. Which leads to more accurate results. Okay, so we can derive the visibility function, which literally just like 0.5. Okay, so I don't understand this maths really. In my note, what do I say? I say x plus the heaviside function. Okay. Okay, so I'm going to take that and kind of throw it in here. Remember, is the, sorry, it's heaviside, isn't it? Heaviside function, where we are, it's either 1 or 0 basically based on a value. So I want to simplify this just for myself a little bit by just having a bit of extra information. Okay, so we have the two heaviside functions that take in those two. Okay, so G V L H, which is the half vector, and then alpha, which is the roughness, is equal to fracking hell. So x is the power of plus, which is heaviside, which is a function of v c dot. I'll tell you what, the most important vector function, a vector thing that you need to learn is the dot product. Holy moly, this is used literally everywhere. So x, big X, to the power of plus, which is two heaviside functions, L C dot. That's the classic filing shrine. Don't go hollow out there, guys. whatever you're up to. So this is lambda. Okay, so where the, I don't know what to call this function, the alpha of m. I might have to look this up because this is kind of like super confusing. Like, where's this like lambda function come from? What is it doing? Now obviously it's correlating with masking versus, it's like working out the height, right? And we use a what looks like a trig identity to get out of a tangent squared situation, and then we can replace cosine. Okay, so we're just simplifying everything down. So this looks like, if I was to, this looks almost like, it's not quite though, a trigonomic version of the quadratic equation. It feels very similar. So this may be like a standard equation. Let's go into Google Images and see if it kind of comes up with something with this particular guy, right? Because this is probably something, oh, Wolfram Alpha or something. Wolfram Alpha, but go and Google Images first, right? It's the first step. Yeah, it's still good for image search in Google. Honestly, it's like, oops. Yep. What is this? Yep. Okay, so I believe the AI here because it's probably so. The formula typically appears in optics and physics, which is correct in the context of modular as calculating the modular transfer function or phase shift. No. I don't think it in interfermo. No, I don't think that's it. Right, let's go into the actual paper, right? At the very least, this will be able to, we'll be able to see. So we need Hertz 14. Oh, we jumped around there. So what are we saying in Hertz 14? Go on. So understanding. There's no link. How annoying. Well. So I'm not going to read this whole thing, but what I want to see is like where this formulas, where this things come from. Yes. There it is. There's the rendering equation. I can't see it, to be honest. I'm looking for... Okay, so this is looking more like it, right? So this, we at least see the heavy side function. Right, so there's that. Lambda. And I remember the first Unity tutorial years back, and the guy started talking about quaternions, and my thought was, okay, this is not beginner stuff. I mean, yeah, if you bumped into quaternions immediately without any background in like any maths at all, it is a weird maths topic. You don't really learn this, even if you went to university. I wonder when you come into contact with quaternions in like university level maths, because I don't think you learn it at A level. Oh, is it your first tutorial? Oh my goodness, that's terrible. Yeah, Matt, all you have to do, it's actually quite simple, is just imagine that the point, whatever you're trying to rotate, right? Just imagine the surface of a 4-dimensional sphere, right? And then all you have to do is rotate that 4-dimensional sphere. And that's actually like how rotation works in quaternions. Like, that's actually how it happens, if you were to see it. You have a very good maths background. I was obviously joking with that 4-dimensional sphere demonstration. It's quaternions are like, it feels like only really turn up in games for some reason. You understand it now, perfect. Yeah. Just imagine a 4D sphere, and then it rotates, and then that's how it works, right? Easy. Okay, next. Back then, it was a Da Vinci Codes video. I've heard of that. Da Vinci Codes, yeah. Oh, sorry, Da Vinci's Code. Got you. Oh, I see what you're talking about. Sorry, you mean it's the Da Vinci? I thought you were talking about YouTuber. Yeah. Okay, so shall I just accept this maths and move on rather than trying to understand it like 100%? Because this filament tutorial is not explaining it. It's just saying, yeah, bro, these math equations cancel out, and then it turns into this if we take the derivative. I mean, that's a good answer, to be honest. But it's not really illuminating. It's a good answer if you know what pointers are. If you're programming a university set, a pointer just points to stuff. But over the years, I've kind of simplified my understanding of pointers down to, it's just a number. That's all a pointer is. And that number is used to look up something in memory. Ta-da! Pointers. And you may think, oh, so it goes into RAM? No, it's this is why if I was explaining this to someone, every process that runs that has its own unique address space. So it's not like it goes to a specific place in your RAM. It goes into a specific place in virtual RAM. This is to stop processes from overwriting other people's memory, right? If we all had access to the actual hardware RAM, and I decided to overwrite everyone's RAM, then I could crash things. I could disrupt the operating system. I could do all sorts of bad things. So processors have their own virtual RAM, and a pointer is just a number that looks up something in that virtual RAM. Oh, you were 17. Yeah. That's it's pretty rough when you're trying to figure stuff out for the first time. Okay, so I'm not going to find... I don't think I'm going to find anything on here unless I read the whole paper. And... that's unfortunate. I wish it had the explanation of how microfacets are executed in this way. Okay, right. Okay, so we've made a lot of progress today. We have done a lot of good stuff, actually. I think I'm slowly working towards like having nice lighting. Everything's starting to come together. So what I'm going to do is share my Discord server. This link is available for 7 days, just in case anyone's watching this in the future or with live chat replay. But if you do want to join my Discord server, there is a link tied to my channel. It's a permanent link. So yeah, I am going to say thank you all for joining us on this live stream. It's been wonderful as usual. Thank you for all your comments and comments and likes and stuff. But yeah, we're gonna call it here, guys. Just so I can show you, this is what we're up to. Final bit, right? So we're getting there. If I turn off the debug geometry, we're getting there. Things are starting to come together. And we'll keep on keeping on with this. All right. Have a good rest of the day, guys, and see you in the next one. All right then. Bye, guys. Bye. Bye. No problem.